Nothing was under my control. Gonna work. Okay. No. No, but I don't know why this is not working. It's fine. I was just getting started. Okay, there we go. I'm going to sit. Okay. No. Maybe. I don't know. Maybe. Okay, just stay. Yeah. Yes. Hello. Okay. I think we can get started. That around time, right? Okay. First, I'd like to welcome all of you to the first Ramulator and DRAM Bender tutorial. We're very excited to present to this broad audience. I am Ataberk Olgun. I'm a PhD student at Safari Research Group. These are the research areas I'm interested in. That's Nisa Bostanci. She is also a PhD student in the same group. And she's looking for internships for summer, fall 2026. And those are her research interests. And we're happy to talk to you about our work after the tutorial or during the coffee break. This is the link to our website where you can find the agenda and the workshop materials that we will upload as the workshop proceeds. And these are like the faces of and the names of organizers. Nisa and I are going to be delivering the bulk of the tutorial. And Haocong, Ismail, and Professor Onur Mutlu are also helping us with the organization. They're also delivering parts of the tutorial themselves. For the first part of the session, of the afternoon session, we will be talking mostly about DRAM Bender after Professor Mutlu introduces DRAM Bender and FPGA-based infrastructures for memory systems research. And we will have an invited talk as part of the first part of the afternoon session. And in the second session, we will continue with the Ramulator part of this tutorial, where we will also have an invited speaker. And as I said, we're very happy to host two invited speakers, Ranyang Zhou and Haocong now. And we're very happy to have them. With that, I will conclude the basic logistics, and we will continue with Professor Mutlu's talk. And assuming I'll take it when I'm aware. I'm here. So this is your microphone. This is also your.
Okay, everything is my microphone, not the microphones. Okay. Well, welcome everyone. This is our first edition of the Ramulator and DRAM Bender tutorial. It's becoming really important to develop tools for evaluating memory systems. So I'm going to talk about that. But first, I'll complain about the venue a little bit because I think we should not be holding conferences in casinos. It really discriminates against people. I know that there's at least one person who is under 21 who couldn't attend today, and I know that person. And I had to go through security multiple times because I have a laptop on me. I don't know if it was not a good idea, but ACM is doing a lot of mistakes these days, and it should stop doing these mistakes. I'll stop at that. But hopefully you guys agree, and I would suggest that you complain to ACM about the fact that this is held at a casino, which is discriminatory in many aspects. And I will say that one more discrimination. They did not check my ID the first time I attended, which means that they assumed I was over 40, and that's also discrimination. Okay, with that, let's get started. Lift the computer. Okay, we're here for this tutorial, but tomorrow we're holding another tutorial and workshop on some other memory-related infrastructures, which is the Virtuoso. If you're interested in evaluating virtual memory systems, hardware-software interfaces, I'd recommend attending that also. So basically, this tutorial workshop is really about evaluating new ideas for new architectures, and our focus is on memory, since memory is a huge bottleneck. I will give like a high-level overview and also some examples relatively quickly. Ataberk, please stop me if I'm running too much over, because I'm going to run over for sure, but too much is not, let's say, accepted. Basically, how do we assess how an idea will affect the target metric X, right? That's what we would like in any evaluation tool in computer systems, computer architecture. And there are many evaluation methods that are available to us, like theoretical proofs of that, analytical modeling and estimation, simulation at varying degrees of abstraction and accuracy, and prototyping with a real system. This is not working, I guess, here. Okay, and a real implementation, right? A lot of these are not, some of these are not easily available to us as computer architects. Theoretical proof, there are very few things you can prove easily, especially if it's related to performance, energy, etc. Real implementation, it's very costly to do real implementation to test every single idea. So we usually do one of the three things in the middle. And this tutorial workshop is going to be on simulation as well as prototyping and testing, let's say. So we'll talk about DRAM Bender, which is an example testing platform. I'll give you a high-level overview. We'll go into a lot more detail with Ataberk later. But this is an infrastructure that we've been developing to test memory systems, especially DRAM memory, for many years. We first developed the first version of it in 2011. It was not called DRAM Bender at that time. And now we can actually test many different types of memories. And this is the lab we have at ETH. We have about 100 plus FPGAs. I don't know the exact number, where we can test a lot of DRAM chips and uncover different functionalities and uncover different problems. It's fascinating to me because we're discovering a lot of issues in a technology that's been around for more than 60 years. It's an old technology for many definitions. In fact, when we first started looking at DRAM, we got a lot of criticism saying, why are you looking at DRAM, right? It's going to be dead. Well, it's not dead yet, and it's not going to die anytime soon, in my opinion. It will evolve into the future, maybe become 3D, etc., but it'll be DRAM. It's good to work on other technologies also, don't get me wrong. Everybody should be working on many different things in the end, but DRAM is still very important. So we keep building our lab. And this is the DRAM Bender, different types of DRAM Bender infrastructure. This is where we did a lot of the Rohammer experiments at CMU, close by here. And this was the original, let's say, FPGA-based infrastructure that we developed to test retention times. We open sourced this for the first time in 2017 as SoftMC. And that was Hassan's paper in 2017. And more recently, Ataberk did a huge revamp of SoftMC. It became DRAM Bender. It's a very different infrastructure. And now we can actually have different versions of it. So we did a lot of studies on Rohammer. Some other people are going to talk about that. But many people, how many people are familiar with Rohammer over here? Okay. How many people are not? Okay, maybe there are some. So I'll go through this relatively quickly. But this is the fact that you're able to induce bit flips in real DRAM chips by repeatedly activating a row, activating and precharging a row. And because cells are too small and too close to each other, this repeated activation causes disturbance in physically adjacent cells. And if you do this activation enough times, you basically corrupt the data. It's silent data corruption, basically, that happens in DRAM because of a particular access pattern. And we've shown that this problem, using this infrastructure, we actually did a lot of testing. Ataberk will talk more about that. And we understood a lot of different properties about this problem. And we showed that this problem becomes much worse as with newer DRAM technology generations where cells are smaller and closer to each other. Essentially, the noise becomes much worse. And the vulnerability to redisturbance increases by more than 100x. The number of activations needed to induce a bit flip reduces by more than 100x. So that's the original paper, which relied heavily on a non-open source version of this infrastructure. And there are people have developed many security exploits that I'm not going to talk about in this talk. More recently, using the DRAM Bender infrastructure, this is a real DRAM Bender, we discovered another redisturbance effect, which is row press, which is the fact that which is a completely different failure mechanism in DRAM, redisturbance failure mechanism. And the idea is instead of repeatedly activating a row at the maximum possible rate that's allowed by the DRAM standard, you activate a row, keep it open for some time, and you activate it again. This keeping it open, keeping a row active actually causes another type of failure mechanism that we call row press that reduces the number of activations to induce a bit flip by 1 to 2 orders of magnitude. And we quantified this. This is actually an example of a discovery that's made using our infrastructure where we didn't really know what was going on exactly at the device level because there was no work that was at the device level. So it inspired other people in the device community, and they later wrote papers explaining why this is happening. So I think this hopefully shows you an example of the discovery you can make in this infrastructure that can enable us to understand what's going on in a better way. Okay, these are some real results. Maybe Ataberk will go into that. So we actually have argued that to solve this sort of technology scaling problems, you want intelligent memory controllers to develop so that intelligent memory controllers can understand these different vulnerabilities and fix these different vulnerabilities online while the system is in operation. So we have some papers on that I'm not going to go into. And industry has taken notice, and in 2023, SK Hynix published this paper where they prototyped a DRAM chip that has that type of intelligent controller. The idea is every row has an activation counter inside the DRAM chip, and the DRAM chip has some computation logic internally where they count the number of activations that happen to each row. And if the number of activations is greater than some threshold, they take some mitigating action, meaning refreshing adjacent rows so that you don't actually get these row hammer bit flips. This is an interesting solution. It's called per row activation counters. It was standardized in JEDEC in 2024. Some people called that this is the biggest change that has happened to DRAM in the last 20, 30 years or so, which I probably agree with because basically what happened is we added computation into DRAM, right? This is a computation mechanism that's added into DRAM, which is great, I think. The solution the particular solution itself may or may not be as good, and there are actually a lot of papers that I'm going to flash over that are working on that. But the mindset is different, meaning you now have computation mechanisms inside the DRAM to fix some technology scaling problem. Now, if you have computation mechanisms like this in DRAM, why not add some other computation mechanisms to actually accelerate computation and make it more efficient as well? So I think this is a huge change, and I hope things become better over time. So the question, of course, is our solution is good, right? This is a solution to a problem that you can easily avoid because the solution is not good. So then the question becomes basically, okay, you tested and you understood a mechanism. What about new ideas, right? And that's where the simulation tools come in. We've been developing simulator since I was at Ramulator since I was at Microsoft Research, actually. This is an effort for 20 plus years, well, 20 years or so. We're going to talk about that later. And more recently, we have a Ramulator 2.0 that's a much better Ramulator. And using these simulation tools, Ramulator 2, we've evaluated industry's recent solutions, and we published multiple papers on this topic. And we've shown that, first of all, to get the solution right, you need to be very careful in how you configure the thresholds of the solution. Second, once you do that, you have some performance loss and energy consumption. So you need to, and to overcome or to reduce the performance and energy consumption impact of the solution, you need to have an even more intelligent controller inside the DRAM or outside the DRAM, basically. That's the idea over here. The question always is, can we do better? And I think one of the, and I think simulation tools enable this question to be answered in a much better way. So we need better and better simulation tools. Again, with Ramulator, not Ramulator 2 in this particular case, we propose this idea of self-managing DRAM. And I think we really need to re-examine the interfaces we have between computation and memory, processors and memory. Because today, the processor and memory interface is very rigid. Memory cannot do anything by itself. We would like to enable memory to do things like row hammer protection by itself, refresh optimization by itself, scrubbing by itself. So we argued that we want to design the DRAM chip to be much more autonomous. To be able to do that, you need to actually change the interface a little bit. Today, the memory needs to be refreshed. DRAM, for example, is a technology that fundamentally requires refresh, but cannot even refresh itself. The memory controller right now here in this computer, in my pocket, and all of your computers, is sending a refresh command to the DRAM chip saying, refresh yourself, refresh yourself, refresh yourself, refresh yourself. Every 7.8 microseconds. If you have HBM, it's 3.9 microseconds. If you're at higher temperature, it's actually at a higher rate. It sounds a bit stupid because why refresh yourself, right? As a human, I think I can refresh myself. Nobody needs to tell me I need to be refreshed. I mean, sometimes it's good if people tell me, of course, but yeah, I don't need to be told every 3.9 microseconds. Basically, the idea is memory can do things on its own at a fine granularity in different pieces. So if the memory is doing something internally and the memory controller needs to access that part that the memory is doing something on, the memory should be able to say, I'm not going to respond to you, sorry, try again. Basically a negative acknowledgement signal. This simple change can enable a lot of benefits. One is memory can implement optimizations internally that are much more efficient than what the memory controller can enable, because DRAM manufacturers know a lot about their chips. And also, now you can actually change what happens inside the DRAM chip without changing the interface and changing the memory controller, because you have freedom. You have some breathing room to actually do things so it can actually enable a lot more progress in our community. And this sort of ideas can only be evaluated in simulation, because nobody's going to manufacture a chip that actually shows this, at least at the frequencies that we have. Okay, so we have this example also. There's a lot more in my micro keynote talk if you're interested. So there's more to come in both areas. There's still a whole lot we don't know about DRAM. This is a technology that's been around for 60 years, as I said. We don't know how aging works in DRAM, which is very sad, I think. And this is something that's very difficult to do with simulation, I think. Here we need really real infrastructures like DRAM Bender. And we've been working on this. We have some partial results. There's more to do. We have recently discovered that there are other issues in DRAM, like variable read disturbance, that Ataberk is going to talk about. He led this work. And he showed that read disturbance threshold varies unpredictably over time, which makes it difficult to figure out how do you set the thresholds for row hammer protections, for example. And we've also discovered recently, Ismail, who's sitting over there, showed that a single row activation can actually disturb thousands of rows. We call this column disturb. And existing row hammer protection mechanisms don't take this into account. And this is not a huge problem at the moment, but it is a problem. And if it's not solved, it's going to become much worse into the future. And we would like to actually figure out these problems that will happen into the future using our DRAM Bender type of infrastructure, testing infrastructure, such that they don't become huge problems like row hammer down the road, right? It's like vulnerability discovery and prevention. And more recently, Ismail has also shown that read disturbance becomes much worse with processing using DRAM mechanisms. So this is another study that you can do using DRAM Bender type of infrastructure. Okay, I'm going to skip some of these slides, but that's why we built this laboratory for understanding memory and their PhD thesis like this from GIRI. Another thing that you can use this infrastructure for is to understand what the DRAM chips are capable of. Basically, I think of this as discovering undocumented functions or unknown functions in DRAM. And this is fascinating because we've discovered that existing DRAM chips are quite capable. And we've done that by using our FPGA-based DRAM Bender and violating timing parameters. So by violating timing parameters, we've shown that one can copy one row into 31 other rows with almost perfect reliability in real DRAM chips. You just need to change the memory controller, no changes to the interface or the DRAM chip. You can perform the NOT operation, and you can perform essentially all Boolean operations, block bitwise in DRAM. These are documented in multiple papers. These are Ismail's paper, Functionally Complete DRAM and Simultaneous Row Activation. I'm going to skip this one because there will be some talk over it, but I'm going to skip the NOT operation. But I'll talk about NAND, NOR, AND, and OR, just to give you an idea. Essentially, the theory is that if you have two subarrays over here, one having two cells, X and Y, or we're focusing on only two cells in each subarray, X and Y, and in the other subarray, A and B, and this is a sense amplifier, cross-coupled inverter. Now, if you had the primitive to concurrently activate all those four rows, the circuit theory says that the sense amplifier compares the average voltage of A and B to average voltage of X and Y. And if one is greater than the other, the bit line on the greater than the other side becomes 1, the other side becomes 0, VDD over 0, essentially. Now, this idea you can use by manipulating some voltages in the reference subarray. You can compute a function on the X and Y values in the compute subarray. For example, if you actually set one of the cells to VDD and the other cells to VDD over 2, which you can do in real DRAM chips, you compute a function on X and Y, which essentially is an AND function. Why? Because assuming that you have only 3 values, 0, VDD over 2, and VDD, for the average voltage over here to be at the bottom bit line to be greater than the average voltage in the top bit line over here, X and Y need to be both VDD, okay? Which means only if X and Y are 1, you get a result of 1 in the bottom subarray, which means that you get the opposite and value on the reference subarray. So you have AND and NAND, and you can imagine OR and NOR Essentially, this way you can have all these functions. This is circuit theory, and we've demonstrated that in real DRAM chips, you can actually do this by essentially violating the timing parameters. You can open multiple rows concurrently or sequentially. So, for example, the row copy operation, by violating the activate to activate timing parameter, you can open multiple rows sequentially, and you can copy one row to anywhere between 1 to 31 rows. And this happens at almost perfect reliability, 99.98%. Maybe you can even employ this. I'll remind you that DRAM chips are not designed for this purpose. We're abusing them to get these results. And NAND, OR, and NOR are not as, let's say, reliable, but we see significant reliability success rates in these. For example, in this particular case, we see more than 94% success rate, which is, of course, not what you want. Ideally, you want perfect reliability. But our goal is to demonstrate that even if you don't do anything to the DRAM chip, you take it as is, it's designed for storage, you don't change the interface, you don't change the DRAM chip, you change the memory controller to violate the timing parameters, then you get these computation functions. Now imagine what you could do if you actually change the DRAM chip to do robust computation. And that's the fascinating research that needs to be done, in my opinion, to enable the DRAM chip to do computation. So this sort of infrastructure actually has attracted a lot of interest from DRAM manufacturers, these results, because they didn't even know, as far as we know, that their chips were as capable as what we demonstrate in these papers. So there's actually benefit for industry to use. Industry is actually using some of these infrastructures as well. Okay, how much time do I have? 10 more minutes. Okay, I have a lot of time. Okay, I'm going to also talk about some prototyping platforms that Ataberk developed. This is PyDRAM. It's not based on DRAM Bender, but we have a version of this that could work with DRAM Bender going into the future. Easy DRAM, I don't have the slide for it. But essentially, it's an infrastructure, FPGA-based infrastructure, where we demonstrated that you can run a program on this RISC-V processor that's on the FPGA, and we changed the memory controller. RISC-V processor can offload a page copy operation to the memory controller, and the memory controller violates the timing parameters and copies the page from one row to another row. And the operating system is designed to actually allocate the destination page in the same subarray as the source page. So with this whole system design, you can actually demonstrate end-to-end benefits to some of the operations that you can do in commodity DRAM chips by changing essentially the memory controller and the interface and the operating system. We've also shown that you can actually offload the random number generation functions to the memory controller over here. So you can use this. It's a bit hard to use, I think, but Ataberk is happy to help over here. And you can get real results from real applications. And hopefully we'll have a better version of this at some point. Okay, let me jump into simulation, because I like simulation also. Clearly, DRAM Bender is, but the part of this workshop is Ramulator. And simulation is very exciting, I think. It's the field of dreams, right? And these are some slides that I use in my computer architecture course, which I'll refer you to. In the end, we're architects. Architects are dreamers, creators. You're in Pittsburgh, so I hope you guys get a chance to visit Falling Water down the road. We went there with my students yesterday. And that's a piece of architecture that's dreamt and created that no one has done, right? And it has its own benefits and downsides, trade-offs, basically. And simulation is a key tool of the architect. That's true for real architects also, not just fake architects like us or micro-architects. I'm just kidding. We're not fake architects. We're also real. Arguably, we're doing much more architecture than any architect can do, because we're using billions of chips are done by architects over here, right? So simulation allows the evaluation and understanding of non-existent systems, right? And that's what we really want. We want to build a non-existent system of the future. And it enables the exploration of many possible opportunities or trade-offs in that system, many dreams, basically. It gives you a reality check of the dreams also if you do it reasonably and well. It helps you decide which dream is better. It also enables, unfortunately, the ability to fool yourself with false dreams or come up with wrong results, also potential. So you need to be very careful with simulation in the end. I mean, that's true for everything, whenever you design a system also, but simulation is a little bit more vulnerable to this problem because you don't have as much control, right? It may not be a closed loop system because you're modeling something far into the future and you're never going to build it potentially, and you're trying to find multiple choices out of that system you're never going to build. So you don't validate some of the things that you're going to test in the simulator, right? So there are three metrics to evaluate simulator, at least three metrics: speed, flexibility, and accuracy. And usually you can get 2 out of 3 and not 3 out of 3. If you get 3 out of 3, let me know. Speed is how fast the simulator runs. Flexibility is how quickly one can modify the simulator to evaluate different algorithms and design choices. And accuracy is how accurate the performance energy numbers, or whatever numbers, the simulator generates are versus their real design. This is simulation error. And you have limited validation accuracy you can get, as I said, right? You can validate it compared to a real system, but it's difficult to validate it compared to an imagined system. So the relative importance of these metrics clearly depends on where you are in the design process and what your goal is. If you want to build the system 10 years down the road, maybe you care a little bit less about accuracy, but you care about speed and flexibility a lot so that you can explore many options. If your goal is to model an existing system as much as possible such that you can make your simulator better so that you can tweak the existing system a little bit more, then accuracy is very, very important. Maybe you don't care about flexibility as much. Speed is probably important because you want to simulate some things, but accuracy is really important in that case. So you can trade off between these. Speed and flexibility affect how quickly you can make design trade-offs and decisions. Accuracy affects how good your design trade-offs or decisions might end up being. How fast, and also it affects how fast you can build your simulator. That's also important. That's another metric. I didn't put it in the previous one because this is really the design time of the simulator, and that's may take time. Sometimes if your simulator design time takes too long, you may be too you may lose your time to market, basically. You may lose to the competitors. Flexibility also affects how much human effort you need to spend modifying the simulator, basically. If you spend too much time, again, you may be too far from your time to market goals. Okay, essentially you can trade off between the three to achieve design exploration and decision goals. I think making the best of architecture is really being good at all levels of refinement as much as possible, including the extremes. And when to use what type of simulation is important, and more generally, what type of evaluation method. So for example, do we use DRAM Bender to evaluate processing using memory techniques, or do we use simulation? That's actually a very good question, I think. I think we want to use both, but they have different goals in the end, because you have much less flexibility with DRAM Bender. Even though if it's FPGA-based, you're still using real chips. Whereas with simulation, you can imagine changing the DRAM architecture, for example. And we've done that a lot with Ramulator, for example. Okay, so I'm going to stop here and refer you to the simulation lecture, which is like 2 hours in my computer architecture class, where we delve into different types of simulators, etc. And also simulation in other domains. So we did a lot of work on agent-based simulation at the supercomputer scale. And there's actually a lot of similarities between simulation at different levels in the end. Okay, the other part of this tutorial is going to be Ramulator. This is something we open sourced in 2015. A lot of people in academia and industry have been using it. Nisa is one of the major developers and maintainers of Ramulator right now. So she's going to give that part of the tutorial. I don't want to take a whole lot of time because we're almost at the end over here. But our motivation was really that DRAM and memory space is going to be a lot more important. And we need a much more flexible and extensible and fast simulator to explore the design spaces and ideas of the future. And the original Ramulator provided support for a lot of models. Existing Ramulator 2.0 also does that. And you can do a lot of interesting studies with it. And a lot of people have done a lot of interesting studies. Industry has picked it up also. Some major companies have been using Ramulator, starting from the original version. They've been giving us a lot of feedback on both standards as well as many different things. So we've incorporated a lot of that feedback. So it's good to have a community that uses it. And later we're going to talk about expanding that community. So hopefully people are interested in contributing while also enhancing their research using these simulators. Okay, this is free. It can be integrated with Gem5 and other simulators. They're producible. And we've done a lot of studies. Ramulator, this is one study where we looked at interactions of different DRAM types with different workload types. And we basically came up with a lot of interesting observations showing, for example, that going from DDR4 to DDR3 is not good in all cases because your latencies increase and some applications actually lose a lot because of that. Bank parallelism is not fully utilized by a lot of applications. So if you're actually going to a memory that has a lot of bank parallelism, that may not work well unless you rewrite your application or change your data mapping significantly. And spatial locality is still important. And for some class of applications, low power memory can provide energy savings without sacrificing performance. This was shown by other folks also, but we showed that in this particular paper. Okay, we did a lot of rowhammer protection mechanisms using Ramulator and Ramulator 2. There are many other ideas. You can again find lectures that talk about some of these. We actually used to hold this Ramulator project course at ETH. You can find all of this as open source on YouTube. With Ramulator 2, we designed a much better Ramulator. Haocong led this effort. And I will not go through the details of it, but it's a lot easier to use. It's a lot easier to adopt. It's a lot easier to change things. It can still be improved, of course, and we keep improving it. But essentially, it has more features, and we will discuss that later. And you can actually do a lot of things more easily, like memory controller mechanisms compared to Ramulator. And some of the papers that we're going to discuss, like the one that flashed you earlier, was done with Ramulator 2, understanding how industry solutions to rowhammer work and how we can make them better. Okay, there's more to come in this area. And it's good to see that a lot of folks are using Ramulator, use it for redisturbance, but also many other things like processing in memory. Some of the LLM acceleration works use Ramulator, and we'd be happy to support it if other people are interested in using it. We are actually have been supporting people who have asked for support. Okay, we have been doing processing in memory studies using Ramulator also, and we've extended the infrastructure. Some of this is open sourced. We want to do more in this area. So if people are interested in contributing, you're welcome to. And also we have a memory-centric computing systems workshop tomorrow. If you're interested in PIM, there will be a lot of studies in PIM over there presented based on the infrastructure that you see today. Okay, there are some other useful simulators. I mentioned Virtuoso, so we have another workshop and tutorial tomorrow. There are many simulators for many purposes, clearly. I will not go through all of these. This is from my lecture. I will mention one thing that we have designed. This is a bit old right now, but the move. This is a study where we used Ramulator and we connected with ZSIM, which is not easy, basically. More recently, we've connected Ramulator with other simulators that are easier to connect to, like ChampSim or I'm blanking, Gem5, etc. Sniper, yes, Sniper. Okay, but this one is a study that, this simulation study enabled us to look at 345 applications and understand what are the bottlenecks in different applications. And this provides a methodology. And this is also open source. People are interested in who are interested in this sort of processing in memory studies, they can take a look at it. So we have a PIM course also. Another simulator that we're not going to talk about is MQSim, which is our storage simulator. We've incorporated it with Virtuoso. So there's a version of it that has Virtuoso. Does that Ramulator also integrated? You don't know yet? Virtuoso, Ramulator, MQSim all together? Okay. So that's kind of the vision I have, basically. You want to have a good processor simulator, a good memory simulator, and a good storage simulator all together. So, okay. So you can go to the Virtuoso workshop here from Andreas, who's substituting for Konstantinos, by the way. Okay. So there are many more simulators that we keep releasing on our website, on our GitHub site. You can take a look at it. But this is the Virtuoso, and I'm going to end over here. I'm not going to talk about this in detail, but what Virtuoso tries to do is it really tries to design a simulator that's accurate enough and also fast enough so that you can do hardware-software co-design studies, especially related to virtual memory, but more generally between the OS architecture interface. It's an interface that has not been evolving very fast, let's say. And one of the reasons is it's very hard to evaluate things because you need to change the hardware as well as the software. It's difficult to get that holistic evaluation. So with Virtuoso, what we want to do is design a simulator that is not necessarily full system, but it has some of the characteristics of the full system, whatever you want to examine essentially. But it also has the simulation speed of emulation-based simulators. So Virtuoso achieves this goal partially. Of course, it doesn't get all the accuracy of a full system simulator, but it enables you to do design space exploration in a much faster way. And this is a new, fast and accurate prototyping and evaluation framework for software, hardware components of especially virtual memory. And tomorrow, Andreas is going to lead the workshop. So if you're interested, you're welcome to attend. And this is where I'll stop. I'd be happy to take questions. If there are no questions, we'll just... Okay, yes, one question in the back. Yeah, so that's a great question. For Ramulator, you can actually, as long as you have the same DRAM interface, the interfaces that we have, you can use any memory technology. But you can also add new models that have the characteristics of your technology. You may need to add new timing parameters, which we're going to discuss actually in the Ramulator in the afternoon. Nisa is going to talk about how to actually add a new memory model. But Ramulator essentially inherently has nothing really specific to DRAM. You can apply it to phase change memory, which we did actually in the past. You can apply it to STT RAM. You can apply it to any technology in the end, as long as you follow the interfaces that we have. Yeah. And for DRAM Bender, DRAM Bender is of course less flexible, because we are bound by what the FPGA can support. If your memory technology has the same interface as DRAM, like DDR4 interface, then you can test it, of course. But if it has some other interface, then you will need to develop an FPGA that works with that. Okay. Go ahead. Yes. No, my microphone. Yes.
Okay, so I'll try to talk about everything that Professor Mutlu said that I would talk about, given the limited time. I'll continue with a more in-depth overview of DRAM Bender. DRAM Bender is an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. And the reason why we came up with this, as Professor Mutlu mentioned, DRAM is subject to many different failure modes, and there are many different parameters that affect DRAM performance, like manufacturing process variation, temperature, voltage, etc. And these we cannot properly model or easily model analytically or in simulation. Therefore, we need to perform experimental studies of real DRAM chips. And there are open source FPGA-based DRAM testing infrastructures that allow us to do these studies. But when we investigated these, we found that this is right before we published DRAM Bender, basically, that they impose restrictions on the DDR4 interface, so you cannot really perform all sorts of studies that you would like to perform. And they're difficult to set up. Some of them are based on, SoftMC was based on discontinued hardware and software at that point, and it was very difficult to use. And they also had some design decisions that made them monolithic and extending them to support new standards very difficult. And we had 3 design goals to overcome these problems while we were designing DRAM Bender. The first one is flexibility. We wanted to be able to test any combination of DRAM operations using any combination of delays between DRAM commands. We wanted it to be easy to use, so we provided the users with a simple programming interface, which we will go over in the upcoming slides, so that it takes minimal amount of time for you to develop your tests. And we wanted to make it accessible to a wide range of users who may lack hardware design expertise, but still want to test DRAM chips. We also designed it with extensibility as a first-class citizen, which allowed us to port DRAM Bender and in the successive years after we published it to different form factors for DDR4 and to different DRAM standards as well. So to summarize, this is the first publicly available FPGA-based DDR4, 3, and now HBM2 testing characterization infrastructure. This picture shows you one of our setups where we have the FPGA board connected to a host machine underneath through a PCIe interface. And we have a temperature controller setup here that we will go over in the upcoming slides. And basically, this is one of our most capable setups look like. We also have power supply controllers to control word line voltage in this picture. And this is easily programmable using C++ API, so you just have to write some C++ programs using an API that we think is easy to use. But I will, again, as I said, I'll go over it and I'll write and execute some DRAM Bender programs as part of this tutorial. DRAM Bender comes with 6 FPGA-based prototypes out of the box. I listed them here. If you have any of these FPGAs, you can download a bitstream from our public repository and start using DRAM Bender. And the most recent addition to this list is the Alveo U50 boards from AMD. Back then it was Xilinx, now it's AMD. This has HBM2 chips, which could be interesting. There's also, we're also gonna publish support for this card, U55C. This is also an HBM2 board, but it has support for higher density, high memory chips, and also enables you to measure power. So if you're interested in any sort of power study in HBM2, this will be useful for you. Professor Mutlu already showed you some pictures of our laboratory, and we have more than 100 plus FPGAs, but we also have people who maintain the laboratory and make sure we can use it for all sorts of research. Some of them are here. Ismail is here. And these are other honorable mentions of people that we have in the lab that work on DRAM characterization, basically, and work heavily on DRAM Bender. So as I mentioned, DRAM Bender is easy to use. I show you one example here of a row hammer program. Professor Mutlu mentioned the row hammer problem, where repeatedly activating two or one aggressor row causes bit flips in neighboring victim rows. So this is the entire program to repeatedly activate two aggressor rows sandwiching a victim row. So just 12 lines. It tells you something about the ease of use of DRAM Bender, but we will go over this in more detail. So it's easy to devise new experiments, to uncover new insights, and the ease of use also comes with flexibility. And in the paper we published about DRAM Bender in 2023, we showcased 3 case studies to show that DRAM Bender is flexible, supports many different types of experiments. There are more details in the paper that I will not cover as part of this tutorial. I hope you have the time to read the paper to basically understand more details about DRAM Bender design, its API, and these detailed results for the 3 case studies if you're interested. So that's a link to the paper. We will publish all of the material online on the webpage. So if you don't catch this link, don't worry. So far, DRAM Bender has enabled a lot of research. I would say these are just a list of papers that were published that use DRAM Bender, sometimes its earlier version or its even earlier version, the internal version we had. It enabled a lot of research, and I'm proud to see that it happened in the end. Yeah, so this is DRAM Bender. To summarize, it's the first publicly available DDR3/4 and HBM2 testing infrastructure, and we think it's easy to use, and we hope that it continues to enable many studies, ideas, and methodologies in the design of future memory systems. So that's the detailed, per se, overview. I'll continue with some highlights, research highlights that we did using DRAM Bender, but I will stop to take any questions at this point. You have any questions? No. Perfect. So DRAM Bender is a versatile platform. It's widely used for at least 3 types of studies. The first one is understanding DRAM robustness problems. This things like row hammer, row press fall into this area. It's used for uncovering new DRAM functionality. Those processing and memory primitives that Professor Mutlu mentioned falls into this area. And it's also used for learning DRAM internals. We have, I think, in the audience, students of Professor Shahin Angizi in New Jersey Institute of Technology in Jungoan and SNU. They do a lot of work using DRAM Bender, which I'm very happy to see. And there are also other people that use this. And again, as I said, I'm very happy to see people use this, and I'm very happy to help you set this up and support you in using DRAM Bender for your own work. These are those lists of papers that are categorized into these 3 main types of research that is done using DRAM Bender, just for your reference. And there are other noteworthy use cases that don't fall into those categories. The first one is understanding DRAM voltage and latency sensitivity, DRAM power characterization, and parts of DRAM Bender was reused in other new FPGA-based infrastructure for other purposes. So I'll give some examples from each type of studies, starting with understanding DRAM robustness problems. I'll give you an overview of variable read disturbance just to give you an idea, a better idea of what you can use DRAM Bender for. And this is variable read disturbance and experimental analysis of temporal variation in DRAM read disturbance. I'll give you just a quick background on DRAM, and as we move on, I'll deepen this background so that no one misses anything. So this is a typical DRAM-based computing system. It's the CPU and a DRAM module attached to the CPU. The DRAM module contains multiple chips, and each chip has many DRAM banks that share a common chip interface, chip I/O interface. Inside a bank, you have many subarrays, and inside a subarray, DRAM cells are laid out onto a two-dimensional array of word lines and bit lines. These cells are connected to what we call a row buffer, or an array of sense amplifiers, from where we can read data and write data to. We've already seen what read disturbance is. So repeatedly activating a row many times, an aggressor row many times, will cause bit flips in its adjacent DRAM rows. This is row hammer. And there's also row press, which induces bit flips by keeping a DRAM row open for a very long time instead of repeatedly activating it. So why do these bit flips occur? To understand that better, we will look into DRAM charge leakage or cell leakage. Each DRAM cell encodes data in fundamentally leaky capacitors. So there are a number of, so this is how a DRAM cell looks like. You have the capacitor in red that stores data as charge in a capacitor, and then there's an access transistor controlled by the word line. If you enable the word line, the capacitor gets connected to the bit line, shares its charge with the bit line. And the sense amplifier not shown in this picture, connected to that bit line, will sense and amplify the voltage deviation on the bit line to read out the cell. So there are a number of, because this is a capacitor, there are a number of leakage paths by which charge can enter or exit the circuit. And the important thing to note here is that the stored charge can become corrupted if too much charge leaks. That's to say, basically, if the capacitor voltage degrades too much. This is a simplified diagram of the capacitor voltage over time. Here we see that voltage decreases over time in an exponential decay. And there's a threshold Vmin under which we can no longer guarantee that we will be able to correctly read the value stored in the cell. As long as we are above this line, we consider this a retention success. And as soon as voltage drops below Vmin, this is an issue. That basically this is a retention failure. And in order to prevent those failures, we have to periodically refresh our DRAM chips. And the interval between refresh operations, we refer to it as the refresh window. Now let's look at the same diagram. What happens to the capacitor voltage in context of a row hammer attack? And again, this is a simplification. This is not really talking about the underlying device level mechanism, but it's one way to understand. It's a good way to understand, reason about how these bit flips could happen. If we repeatedly activate a neighboring row, we will accelerate the charge leakage to a point of failure before the first refresh command in this diagram is issued to the DRAM chip. So any successive refresh command in this diagram will read the incorrect value and store the incorrect value back to the cell. That's one way to think about how we get row hammer bit flips. And to prevent these issues, prior works proposed many different techniques to mitigate read disturbance bit flips. And they each come with a different reliability, performance, energy, and area trade-off. But a common operation pattern across many of these techniques is that they take an action before a bit flip manifests. And an example to that action is preventively refreshing a victim row. So before enough charge leaks, you refresh the row so that the charge basically goes back to being at a very high state. And to do this, they must accurately quantify the amount of read disturbance a row can withstand before it experiences a bit flip. And this is typically quantified by time-intensive testing for read disturbance bit flips. And the read disturbance threshold, or RDT for short, quantifies the amount of disturbance a row can withstand. And this metric is typically expressed in terms of an activation count. So now I will try to illustrate why it is important to accurately identify this value, RDT. The x-axis here shows you increasing RDT values in arbitrary units, and the y-axis shows you the performance and energy overheads of read disturbance mitigations, again in arbitrary units. And this is a curve you would expect to see. As RDT becomes smaller, we perform more and more refresh operations, and that comes with an additional performance and energy overhead. If you have this ground truth RDT value for your chip, you want to configure your solution with this exact value. Why? Because if you configure it with something higher, then you cannot guarantee that you would mitigate bit flips. So your system is no longer secure. If you configure it with something much lower, you will have to induce unnecessary overheads from mitigation operations. So in summary, we must accurately identify the redisturbance threshold to securely prevent bit flips at low overhead. And prior works assume that the ground truth threshold, this redisturbance threshold value can be identified. And in this work, we challenge this assumption. And our goal is twofold. So first, we would like to understand if the redisturbance threshold changes over time. And if so, how reliably and efficiently can we measure it? We also want to analyze implications of temporal variation of redisturbance threshold for redisturbance solutions. And for that, we use DRAM Bender, which you've seen already many times, and we test many chips. And the key takeaways from our study, from this study, is that the redisturbance threshold of a row changes unpredictably and randomly over time. And this makes accurately identifying the redisturbance threshold very challenging. This is, I'm going to show you one of the key observations we made in this paper, and I will move on to the next work. So this is the redisturbance threshold values observed across many measurements on the x-axis. And this is an example point in this plot. This depicts one measurement. And this yielded a redisturbance threshold of around 37,000 hammers. This is across 5 measurements, and this is across 1,000 measurements. And this is basically those 1,000 measurements summarized into minimum, maximum, and average points. And this plot shows you those measurements across 100,000 times. And here we see that for this series of redisturbance threshold measurements, the absolute minimum value appeared at around 17,000 measurements. So it took us 17,000 times to get to that, to find exactly what that minimum value was. And this is a key result that demonstrates the variable redisturbance phenomenon. We, of course, tested many chips, and the distributions, I show you some of them here, the redisturbance threshold distributions from many chips. I won't talk about this in detail given the limited time, but we did test to see if these variations in the redisturbance threshold was truly unpredictable. And based on the methodology we applied, we think they're likely unpredictable. And for details, I have to refer you to the paper. We also performed a much more in-depth study of VRD by varying many test parameters, which DRAM Bender allows you to do. You can test for different temperature levels, you can use different row open times, and you can test many DRAM rows if you want, using many different data patterns as well. The key takeaways are these from that in-depth study. Basically, all of the tested chips that we have are subject to VRD. That's one takeaway. And if you want to rely on a few measurements to determine the minimum redisturbance threshold, we find that you're likely not going to be successful. So you need a lot of measurements in the end to find the absolute minimum value. And data patterns, temperature, and aggressor one time, these parameters all affect the way VRD behaves. This VRD phenomenon has important implications for redisturbance mitigations because you cannot reliably identify the minimum threshold value accurately given a limited amount of testing time. And we evaluate short-term solutions for VRD, like using a guard band for your observed redisturbance threshold value, combined with error-correcting codes. And the preliminary, I will say, the results show that if you use a guard band that's larger than or equal to 20% for your redisturbance threshold, you will find that you only have one unique bit flip in a tested row. This is based on our limited bit flip data set. So it seems like ECC combined with guard bands that are relatively high would prevent this issue. But we also think that you have to test for more, test more chips and test for more iterations to understand the limits of guard bands in ECC, because these numbers that we've found can only get worse with more testing per se, but they cannot get better. An extended version of this paper is on arXiv, and I invite you to read it if you're interested. I will not talk too much about row press. Is another work that we did in this direction of understanding DRAM robustness issues, which Professor Mutlu mentioned. Basically, if you keep a row open for longer, you can induce bit flips with fewer activations in a row hammer sort of attack. I will mention that we also demonstrated that you can get these bit flips in real systems. If you access consecutive cache blocks that are mapped to a single DRAM row, you can figure this out by reverse engineering these mappings. You can keep, we hypothesize that you can keep a DRAM row open for longer. And if you do that, you will get bit flips with row press where you couldn't get bit flips with row hammer. And again, I invite you to read the paper for more details on that. I'll talk a little bit about column disturb, which is another work we did very recently in the same direction. So just to remind you how a DRAM subarray or DRAM bank looks like, we have many subarrays. We have cells laid out onto a two-dimensional array connected to sense amplifiers. And we call a bit line that spans in this work, at least in the context of this work, we call this bit line, we refer to it as a DRAM column. So we asked the question, what if there is like a much worse redisturbance phenomenon that affects thousands of DRAM rows through bit lines or through columns in this work? And it turns out there's one that's called column disturb. If you repeatedly open this aggressor row here, you will disturb the voltage in the cells or the charge stored in these cells that span these three subarrays, because if you notice this back-to-back inverter or the sense amplifier connects this column, if you can see my pointer, to this column as well. So a cell that is in the middle subarray in this picture is actually connected to some extent to all of these other cells and two neighboring subarrays as well. So by repeatedly hammering this, you disturb the charge across all 3,000 cells in this example. These are the key takeaways, 5 key takeaways from our characterization study on column disturb. I'll show you the results for the first one, which I think is the most important one. It's a widespread redisturbance phenomenon and becomes worse as DRAM technology scales down to smaller node sizes. So this is, on the y-axis, we show time to induce the first bit flip in a subarray in milliseconds. And the x-axis shows you different DRAM die divisions and densities. And each subplot is dedicated to a manufacturer that we list on top of the plot. This is the result. We conclude from here that all tested chips are vulnerable to column disturb. These are not retention failures. These are caused by disturbance errors. And in the paper, you can find more details about how we distinguish between those. The second observation is that newer DRAM chips tend to be more vulnerable to column disturb bit flips. And this trend is also consistent across all tested manufacturers. And finally, we see in some of the tested chips, I think this is in one of the chips, we find bit flips, column disturb bit flips under 64 milliseconds. Now, 64 milliseconds is an important number because that's the refresh window for this operating temperature that these chips were subjected during testing. So this means we have accelerated charge leakage to the point where things started failing during nominal retention periods. So I'll leave you with that. And for more details, I refer you to the column disturb paper. And I'll move on to the other type of studies that DRAM Bender enables. This is uncovering new DRAM functionality, which Professor Mutlu talk about to some extent. I'll start with QuackTRNG. This is a high throughput two random number generation using quadruple row activation and commodity DRAM chips. This was published in 2021, and we used an internal version of DRAM Bender to conduct this study. I'll give you a little bit more background. We've seen this picture before. This is a capacitor attached to a sense amplifier through the access transistor, and the word line controls this access transistor. When it's enabled, the capacitor connects to the sense amplifier through the bit line. And there's a bit line bar on the other end, on the other terminal of the sense amplifier, and it has an enabled signal. So how does the charge sharing process happen, or how do we access the cell actually? We first enable the word line that connects the capacitor to the bit line. The capacitor shares its charge with the bit line, and the bit line voltage starts deviating towards VDD in this example. which will be picked up by the sense amplifier and amplified to VDD. And doing so, we also write the data back to the capacitor. And if you look at how this works at the granularity of a single cache line, which is a collection of many DRAM cells, and we look at this because DRAM data transfers happen in the granularity of cache lines in today's systems. We need to send an activate command, which will enable the word line of this first basically row that's indicated with blue over there. And this operation basically enables the word line for all of the cells in this row and connects the cells to the sense amplifiers. Now we can send read commands to read data out of this subarray or this bank at the granularity of a cache line. So each read is a cache line read. If we want to access a different row or different cell in a row, we have to pre-charge this bank, which disables the word lines and pre-charges the bit lines. And then we send the activate command to the other row. We can repeat the read operations. There are timing parameters that we must obey to guarantee that the DRAM chip works reliably. And those are the important ones for this work are TRAS, which is also called the activation latency. It's the amount of time we wait between an activate command and the subsequent pre-charge command. And there's TRP, which is the pre-charge latency. And that's the amount of time we wait between pre-charge command and the next activate command. And we have to obey these because we want to guarantee that the DRAM chip has enough time to conduct all these analog and digital operations inside the DRAM chip. We made a new observation in this work that if you carefully engineer DRAM commands, a sequence of DRAM commands, you can enable 4 rows in real DRAM chips. And it's actually quite simple. What we do is we send an activate command. Then instead of waiting for the default 35 nanosecond time delay or timing parameter, we greatly violate that timing parameter and we wait for something smaller than 3 nanoseconds. And we send the pre-charge command, and then we again violate the pre-charge to activate timing parameter. Again, by a lot, like by a very huge margin. And this causes us the DRAM chip to activate 4 rows instead of, in this case, we send 2 activate commands. You would expect 2 rows to be activated sequentially. What happens is 4 of them get activated at the same time. And why does this work that way is, to explain this, we have a hypothetical row decoder circuitry that is based on the use of hierarchical word lines in DRAM chips, which basically are there because you have a lot of huge high density and performance requirements for these DRAM chips, today's DRAM chips, and designers use hierarchical organization to provide high density and low latency DRAM operation at the same time. I'll show you how this looks like in this figure. There are word lines that we call the master word line. Each of these will drive multiple local word lines. So these show you, so here I show you 4 local word line drivers and 4 local word lines that are connected to 4 DRAM rows. And we think that a local word line is driven by a combination of these select signals that I will show you how they work in the next slide, and the master word line. So let's see how these operate to enable 4 DRAM rows with 2 activations. So here we have the hypothetical row decoder made up of 2 stages. On the left side, we have our address bits, row address bits, 2 of them, the least significant address bits. And on the right side, we have those 4 select signals in the previous figure. In the first stage, we pre-decode the least significant bits into 4 signals. And the second stage, we will drive these control signals by combining the address bits. So here we have a NOT gate, basically. And basically, we're pre-decoding the address bits, right? So we have A0 bar, that's address 0 negated, and A0. We have the same for A1. And then we latch these signals. And we reconnect them to form the select signals in this way. So A0 bar is connected with A1 bar through an AND gate to form the S0 select signal. So let's see what happens when we issue the address sequence, the command sequence that we talked about earlier to this circuitry. First, we send an activate command to row 0. So both of these bits are 0. And the first latch, the latch driving A0 bar and the latch driving A1 bar gets driven per se. Then we also, you can also notice that these two select signals here, the AND gates that drive them are partially enabled also. So the first activate command drives a single word line. It doesn't drive 3 word line. It partially drives 2 word lines. It drives a single word line. When you violate the timing parameters greatly and send a precharge command, we hypothesize that the precharge command simply doesn't have enough time to disable these latches, or the DRAM chip doesn't have time to disable those latches reliably. And then when you again violate the timing parameters and send the second activate command, now what happens is these bits on the left side transition into 1, which sets these 2 latches. And when those 2 latches are set, we have the whole circuitry on the right side basically enabled, because they're a combination of they're an AND combination of 2 signals. So all 4 word lines get enabled. That's how we get quadruple activation basically. So you can use quadruple activation for true random number generation. And true random numbers are critical for many applications, including cryptographic applications, scientific simulations, and even machine learning. And you can find more details about the use of true random numbers in Quark TRNG paper. But I'll show you how we can generate true random values using Quark or quadruple activation. This is 4 cells, simultaneously activated cells on a bit line. We initialize them with conflicting data patterns such that row 0 and 2 are initialized with a logic 1 signal, and rows 1 and 3 are initialized with logic 0 signals. When we send the first activate command, this is the voltage on the bit line, basically. We send the first activate command to row 0. That cell on row 0 starts sharing its charge with the bit line, so it loses some of the charge. The bit line gains a little bit of a charge. And then we send the precharge command and activate with the violated timing parameters. Now this enables all 4 word lines at once. And because the bit line voltage does not exceed the reliable sensing threshold, which we depict as VTH in this figure, this will the sense amplifier will randomly sample due to random perturbations on this bit line voltage, the bit line to either VDD or minus VDD in this picture, or you can imagine that to be 0. So if you have enough of these cells, you can generate random numbers at very high throughput, but I won't go into the details of how we do that. I'll show you just this picture, which shows that Quark TRNG beats state-of-the-art DRAM-based random number generators in throughput. And especially as data transfer rates scale to higher values, you get better improvements over prior work. So that's Quark TRNG. We also have recently developed Simra TRNG, which was presented in ICCD last year. And I'll just show you this from that. If you can actually simultaneously activate more than 4 rows or fewer than 4 rows if you want. And that can get you a higher throughput because of basically the randomness. I'll just use the word randomness you can extract out of the bit lines increase with the more rows you activate. So that's just something I wanted to mention. I'll skip FCDRAM in the interest of time, and also because Professor Mutlu already talked about this. And I'll get to the last type of work that is DRAM Bender enabled, which is to learn DRAM internals. I'll give you the example of uncovering in DRAM row hammer protection mechanisms. So we already know what row hammer is. There's something called target row refresh that DRAM manufacturers introduced in DDR4. The vendors equipped their chips with some proprietary defense mechanism known as target row refresh. And the key idea here is through a proprietary sampling mechanism, the circuitry in the chip, the TRR circuitry in the chip, will sample some of the DRAM rows, repeatedly activated DRAM rows, as aggressor rows. And when the memory controller sends a refresh command, these are periodically sent, the TRR circuitry will perform some victim row refresh operations hidden behind the latency of periodic refresh operations. So this is completely abstracted away from the user, in this case, the memory controller, happens in an overlapped way with the refresh operations. In this work, our goal was to understand in DRAM TRR and assess how secure they are and potentially bypass them and enable a path towards secure DRAM row hammer mitigations. And the key idea in this work is to use data retention failures as a side channel to detect when a row is refreshed by on-die mitigation mechanisms. And I'll show you this over a toy example. We develop an experiment using DRAM Bender to basically uncover what sort of sampling mechanisms these TRR techniques use. So first we find the DRAM row R with a retention time of T, and this means that the row will harbor retention failures if we do not refresh its content for T units of time. On the bottom you see a timing diagram or timeline where we show actions taken by us, the experimenter, and the currently hypothetical on-DRAM die mitigation mechanism. So initially the row R is refreshed so it can retain data until time gets to T here. We wait for half T and we activate and precharge R+1, which is adjacent to this victim row R once. And let's now look at what a hypothetical mitigation mechanism would do. It would sample the hammering of R+1 as an aggressor row activation. And then we issue a periodic refresh operation. If you remember, these trigger these mitigation mechanisms. And if the mitigation had sampled R+1 as an aggressor row, what's going to happen is it will refresh R because that's the victim row, assuming it exists. And then we wait for half T, and then we read out row R and check if there are any bit flips in R. So the key idea is that row R will experience no bit flips only if an on-DRAM die mitigation mechanism exists. And if it doesn't exist, it will be, since it was not refreshed at half T, it will experience retention bit flips at T. Now, this is much more complicated than how I explained it here because retention times are also subject to random perturbations. So retention time of a cell will change with time randomly. That's due to the variable retention time phenomenon that's widely studied. And yeah, the details, you can find the details in the UTR paper. We have used this methodology to characterize the mitigation mechanisms implemented in various different chips. And we crafted new patterns, access patterns that reliably bypass these mechanisms and induce bit flips in real DDR4 chips. And for more details, detailed results, I'll refer you to our paper. But we basically bypassed all the mitigation mechanisms. That's what this is showing you here. And I'll also highlight DRAM scope as another work that is in line of this learning DRAM internal type of studies that DRAM Bender enables, but I will not spoil it for you because Haocong, the first author, will present it later today. And I'll conclude the research highlights section of the tutorial. So DRAM Bender enables many studies, ideas, and methodologies in the design of future memory systems. And hopefully this short presentation convinced you that this is the case. We attribute this widespread success of DRAM Bender to its flexibility and ease of use. And we believe that research drives new DRAM Bender features and improvements. So we welcome everyone to try this out and ask us if you need any help setting it up. We didn't have the support we have today, the variety of DRAM standards that we can test today a few years ago. So these are all enabled by really the new research ideas we want to pursue. Okay, so that concludes the research highlights, which takes me to the live demo, which will for sure succeed because that's how live demos work. Before I get to executing some DRAM Bender programs, I'll give you an overview of the demo. So we will connect to one of the host machines in our lab, Safari-FPGA-45, and execute, obviously, a row hammer program. And we will vary the program parameters and see the effect on a real chip. And I'll also explain to you how this program gets executed through the DRAM Bender hardware. So a typical DRAM Bender test will follow this workflow. So you in a C++ or a Python executable, you do 4 things. First, you initialize the DRAM Bender platform. This will become clear in the upcoming slides. Then you create a DRAM Bender test program. Then you execute this and then read and analyze the experimental data. So just as an aside, I will talk about how transfers between the host machine and the DRAM Bender FPGA works. So from the host machine, we send programs to the FPGA card and to the DRAM Bender in the FPGA card, and we receive data back, experimental data back from the FPGA. And this is done through a PCIe connection. And the drivers we use, these are installed as part of DRAM Bender, so you don't need to worry about these details. But I just wanted to talk about this because this is an important part. Host to card transfers, basically from your perspective, that's writing to a file. And card to host transfers, data transfers, are just reading from another file. So these are the 2 file descriptors that the driver registers to your machine when you have successfully connected an FPGA board with DRAM Bender in it. And so I'll show you the code that corresponds to initializing the DRAM Bender platform. And my struggle begins. So let me see. Okay, so you can see a Visual Studio Code screen here. I hope the live stream also sees it. Can we check? Okay. Does it work? Okay. Does it look good? Okay. I'll zoom in a bit. Perfect. So creating a platform is very easy. That's just basically initializing this object, a softMC platform object. It's called softMC because of legacy reasons. It's not called DRAM Bender, it's the early version, but that's not important. You create this platform object that will handle everything about the PCIe transfers and all sort of bookkeeping that needs to happen in the background, and you will forget about it after that. You call the init function, and if this succeeds, you're ready to send your programs and get your experimental data back. So that's how you initialize the platform. Now we will create a test program. But before we go there, I'll describe you the programming model for DRAM Bender. It's assembly-like programming, I call, using either C++ or a Python API. We will use C++ in today's example. There are 2 types of instructions that you can use to program DRAM Bender. Those are either a DRAM command, that's either going to be a DRAM command batch, a sequence of DRAM commands, or what we call regular instructions, which are arithmetic control flow load store instructions. And there are 13 general purpose 32-bit registers in your DRAM Bender hardware and 3 special purpose DRAM address write registers. We will get to why we have the address write registers later. These are the regular instructions that we use to program DRAM Bender. And I'll now go over the program. But before I do, here's what the test program does. So it's basically split into 4 stages per se. We will create this program by appending instructions to a list. And we will initialize 8 rows that surround the victim row first, including the 2 aggressor rows. Then we initialize the victim row. Then we hammer the 2 aggressor rows. And then we read the victim row. It's quite involved. It's 300-ish lines of code. I'm not going to go over all of it, but I'll show you the most interesting bits. It's also very repetitive in this example. So once we understand the first part, the rest will come very easily. We have a bunch of definitions here. Just think of them as register identifiers. So we will use register 0, 1, and 2. These are the special purpose address write registers. They're not important for now. We have the column address register, shortened as CAR, that gets register number 3, bank address register, row address register for the victim row address register for the aggressor rows, some registers to store our data parents that will write to the aggressor rows and the victim rows, and some registers to keep track of how many times we hammered the aggressor rows. But again, these are things you don't have to remember. It's just so that I explain to you how we program a DRAM Bender program. First, we load what we call a wide data register. This is going to store what gets written to DRAM, the DRAM chip with every write command. So this is a 512-bit wide register, and you initialize this word by word, word being 32 bits. So that's why we have a loop that goes to 16 here. We initialize every word of this wide data register with the data pattern we want to use to write to the victim row in this example. So that's basically two different instructions executed 17 times in total per se. And then we initialize the values for our stride registers. So we initialize the column address stride register with 8 because every DDR4 DRAM read or write command will write to 8 columns, 8 successive columns in the row. So with every read command or a write command, when we set a bit in this instruction, it will tell DRAM Bender hardware to increment that column address register by the value that we put in the stride register, so that we can repeatedly execute DRAM command batch instructions and not wait for arithmetic instructions in between. These are just initializing these registers that we will use for this program. And then we get to actually executing the DRAM commands themselves here to initialize the victim rows or the rows that surround the aggressor rows. We can add DRAM commands to our program like such. So you're still adding an instruction to a list composed of 4 DRAM commands. The first one is a pre-charge command. We want to make sure our bank is in a pre-charge state before we activate any row in it. You tell the pre-charge command which bank it targets. And then there are some additional parameters here that are not important for this tutorial. But you can find all details about these as part of the materials that we've shared so far about DRAM Bender. And you can ask me if you have any questions. Then we add some more knobs. And if you remember, we talked about timing parameters that we need to obey so that the DRAM chip has time to do all these operations. So this is the way we specify timing parameters in this programming model is you add knobs between commands. So the clock frequency for this is going to be 600 megahertz. If I'm not, am I wrong? I think I'm right. So every DRAM command here is corresponding to a 1.5 nanosecond time window. So if you want to have 15 nanoseconds between the pre-charge command and the next activate command, you add so many knobs in between. That's how you can violate or you can obey the timing parameters using DRAM Bender. Then we activate the bank and the row in the bank that we want to activate. Then we basically write to it. So in this example, I'm utilizing both the column address register and I'm doing some add immediate instruction to keep track of how many columns we initialized. So once we get to the end, we repeat this loop to initialize all 8 rows. So this is the initialization routine per se, and we repeat this for the other parts of the program. So I'm going to skip those, but this is basically just initializing the rows, the aggressor row here, the other aggressor row here. These are the ones that we're going to repeatedly activate to perform row hammer attack, and then the victim row here. This all has the same basically instruction pattern. And then we get to the hammering bit, which is only a few instructions. We pre-charge the bank, then we activate a row, the aggressor row 1, and then we will wait for however long we want to wait between the activation and the pre-charge of the row. So this is to basically tune the row open time for row press sort of attacks. So you can keep a row open for however long you want. And this is also another thing that makes DRAM Bender powerful. You couldn't really do this in a real system very easily. While in DRAM Bender, we can keep a row open for 32 milliseconds, which will never happen in a real system, really, unless you have a design bug. But basically, that's constructing the hammer component of the program. You activate a row, you pre-charge it, and then you increment some counters to understand how many times you've activated, keep track of how many times you hammered the row, and then you do this again and again. And then you get to the read victim part, which is basically the same thing as above, where we initialize the rows, but instead of writing to the DRAM row, we read from it. And that is where our program ends. And at the end of each program, you have to append this instruction, SMC end, that will tell DRAM Bender to basically evict everything that it has in the buffers, get every data back to the user. Once you execute this program, and we will execute it soon, I still have 5 minutes, what's gonna happen? So this is a hardware overview picture from the paper of DRAM Bender. And I will not describe this to you in detail. I'll show you what executing a program means. So the host machine, your program will call platform.execute with the program object. And then the front-end module here that's responsible for taking data from the PCIe and putting it in instruction memory will do that, will do exactly that. So your program will get basically copied to the instruction memory in this picture. And then we have two types of instructions, as I mentioned. The regular instructions will take the execute pipeline path. They will be fetched in one stage, decoded in the other stage, and then we have a three-stage execution pipeline. And your regular instruction, like add immediate and all the branch instructions, will go through this pipeline. Your DRAM command batches take the other pipeline, and they get through what we call a DRAM interface adapter that on the left side has a DRAM Bender internal interface to DRAM Bender's programmable core. This is common across all DRAM interface adapters. And we have many DRAM interface adapters for different form factors and for different standards. So we just replace this module, ideally, to support a new DRAM standard. You don't have to touch the rest of the DRAM Bender hardware design. And if you have read commands in your code, in your program, you will write stuff to the readback FIFO. The DRAM, whatever gets back as a read transfer from the physical interface will be written to the readback FIFO. And the end instruction will cause DRAM Bender to flush this readback FIFO and also send a specialized instruction to the software side that tells the software that the program has ended executing, so you can tell the user that. That's how a program gets executed. We will execute the program. Just in the aside, we have this spreadsheet that tells you how instructions are encoded in a more humane way. So if you want to add new instructions or change things in the DRAM Bender, this is something you want to refer to, but we have this a link to this in the README file in our repo as well. So you're not missing anything. And as the last step, you read the data and you analyze what you've read. And that way you can come up with all sorts of new attacks, hopefully, or find new functionality in DRAM chips. So as far as our program goes, where's my pointer? Okay. I already ran this a few times, so I'm sure it's going to work. I just need to find the right, okay, there you go. So what I'm doing here is I have a bunch of other things I didn't show you in this program. Why does this keep happening? Okay. I'm basically hammering victim row 300, victim row number 300 over here, you see. 35 nanoseconds with each activate. So this is a row hammer attack, not row press. And I initialize the aggressor row with a data pattern that looks like 0101, repeated across the row. I initialize the aggressor rows with the inverse of this. So the aggressor rows will have 1010 instead. We target bank 1 and we hammer for 25,000 times. That means we're activating each row 25,000 times. We have 2 aggressor rows. And I'm going to run this. Good. Okay. And then here I have recorded basically the locations of the bits that flip at 25,000 hammers. So as you can see, we have only 8 bits that flip. If we run this again and again, at some point we will see 7, 9, and that's VRD basically. But I'm not going to do that in case I cannot show you that. So I'm going to show you something different. I'm going to add another 0 to the hammer count. By the way, 25,000 hammers take maybe around a few milliseconds. So this is not the retention time yet. This is not 64 milliseconds yet. Even this is not 64 milliseconds. So we've hammered for 250K times. And if my PhD thesis is correct, there are going to be many more bit flips. So there are many more bit flips. These are all real bit flips. This is not fake. Basically, almost everything flipped at 250,000 activations. So if you don't believe row press, I'll show you it's real. With 25,000 activates, we had only like 8 bit flips, right? That was for T agon equals 35 nanoseconds. If you make it 3.5 microseconds, that's gonna, again, if Haocong's thesis is correct, this is going to have many more bit flips. So as you can see, you have bit flips all over the place. So that's just like a short demonstration of row press and row hammer. And I think I'm done right on time. So if you have any questions, I can take them for 2 minutes. I'm sorry, Ranyang, can I take a few more minutes of your time? Okay. Do you have any questions? Yes.
So what I understand is we are generating assembly code through C++ API, right?
Yeah.
Yeah, now I see. Yeah. So we are generating assembly code through C++. I was wondering, is it possible to directly write the assembly code, or is it too complicated to write that?
No, we had at some point, we were developing like a parser for DRAM Bender assembly like code, but it's still, we left it in an experimental state. So I mean, if you're really interested in this, we will be very happy if you want to work on this, and we can integrate that parser or something like that to the repo. Maybe which will make it easier to write programs. Yeah. Thank you. Okay. Thank you very much for your attention. I invite our next speaker. But yeah, thank you. I'll maybe introduce you. Yeah. So just give me a second. Yes.
This one can make it works.
Let me open your slides and then can you introduce someone? Thank you.
Okay, so the next speaker is Ranyang Zhou. I hope I pronounced it correct. He's a PhD candidate in electrical and computer engineering at the New Jersey Institute of Technology, working with Professor Shahin Nangizi. His research focuses on processing in memory and DRAM-based attack and defense mechanisms for machine learning systems. And his recent research investigates DRAM fault injection attacks, including row hammer and row press, and their implications for the reliability and security of AI systems, aiming to enable robust and secure next-generation computing platforms.
Thank you for the introduction. And unfortunately, Shahin could not make it due to some a last-minute commitment. So I will represent him to do the representation. And I will share 2 of our work, which is accepted in CVPR 2024, and the other one is accepted in date 2025. And I will follow the talk roadmap to show everything to you guys. And first, let me start from why do memory attack on DRAM matter. The core security gap is that due to the DRAM are deployed in safety critical applications such like autonomous vehicles, medical imaging, financial system, security system. Many researchers have assumed that the attacker have access to the training pipeline, which this is not a realistic constraint in real-world production deployment. As a result, inference stage threats that exploit hardware-level memory vulnerabilities have been significantly overlooked by the research community. So I'd like to share how to use DRAM benders in the real applications in our work. So training stage attacks follow a four-step pipeline. The attacker first poisons the training dataset by injecting trigger stamped samples, causing the module to associate the trigger pattern with the target class during training. And after the deployment, the module behaves normally on clean inputs, but will misclassify any input which contains the stamps. The key limitation of this attack is that they do require access to the victim training facilities. But inference stage attacks by contrast requires no access to the training process. The attacker may reverse engineer module weights and architectures with white box access. They injected bit flips into DRAM at inference time via hardware force, such like a rowhammer, to do the bit flips. And the end result is the same. The module will show the correct result with a clean input, but will be misclassified with the stamped figures. The fundamental distinction is that these attacks do not need any access to the training stage. We propose that the attack does not need to modify the module directly. Instead, by flipping the bit in the PFN, which is the page frame number, the physical pointer is the operating system page table. They redirect a virtual address from the original weight block 1 to a replacement block W2, already existing in DRAM. On the other hand, notice that the threat module is deliberately minimal. The attacker needs white box access and the ability to trigger rowhammer without any training access or hyperparameters. So these three figures will show from the low level to the high level what the attack mechanism is. So on the left side, the figure 1 shows that the hardware mechanism. The attacker uses rowhammer to bit flips in the PFN. We can see that the original page table A1 will correctly mapping to the target row W1. But after a single page frame number bit flips, A1 silently redirected to the A2, which point to a replacement block W2. The DNN loads W2, still thinking this is W1. No weights are directly written. No training pipeline is touched. It is a pure memory addressing exploit. So on the top left, figure 2 shows that how the attack looks like at inference. A clean input still produces the correct prediction. The module behaves normally with the clean input, but with a triggered figure will be misclassified to the attacker's target class. So replace the weight blocks makes the module secretly to show different results. And the function we are showed in the bottom right figure. It shows the hard work actually happens offline. The attacker will use their functions to select the figures which using the combinational loss function to optimize the stems and the layers, everything parameters they need to reduce the accuracy in the module. And finally, the actual hardware bit flips, when it comes, it's just the need one operation. And the interference is totally decreased in the DNN. And the algorithm takes takes as the input a pair of clean and triggered images, the DNA itself, and weights as input. And the attack proceeds through 3 sequential strategies. Strategy 1, target block identification. Rather than searching all the module weights, DeepThroat identifies the most attack-relevant weight blocks by ranking them according to the function we introduced previously. And we can calculate according they are gradually vulnerable with respect to the Trojan loss. And we find only the top 5 blocks from the last 5 layers are selected, since the later layers have the most direct influence on the classification decisions. The strategy 2 is that how to replace the block search. The selected target blocks are optimized to an ideal weight update. Since the arbitrary weight synthesis is not allowed, the algorithm then searches existing memory for the for the feasible blocks that mostly close to the ideal module. And finally, triggered enhancements. So how many stamp is needed on the figure is very important. If the stamp is too large, it is very easy to be recognized by the defense mechanism. And with the loss function, we find a balance between the trigger and the original figure to jointly minimize over the both weight target and the trigger target. Then this is the experiment. Our group follows the step-by-step with the ETH group's tutorial. And we have a host machine and connected the FPGA. We use the Avalon U200 FPGA. And the DDR4, we selected Samsung chips, which mostly used in many servers. And also, we hold a temperature controller to exclude the temperature's influence in our experiments. And with the experiment setup, we can show some results in Cypher 10 and Cypher 100. On Cypher 10, the attack exceeds 97% attack success rate on 4 out of 6 module architectures, with ShuffleNet V2 reaching a perfect 100%, and most of them falling between 97 and 99% attack success rates. And critically, the impact on the clean accuracy is negligible. The maximum accuracy drop on Cypher 10 is less than 1 over 10,000, which means the attack is very, very hard to be observed by the defense mechanism. And all this is achieved with only 5 hardware iterations, which means we only need to change 5 physical address to make this. And next we test across 9 diverse architectures. So we can see that DeepThroat achieves near perfect attack success rate on all modules, with clean accuracy remains virtually unchanged. And in VIT, with the last one, we can see that we achieve 100 attack success. And compared with state-of-the-art comparison against the CNN modules on Cypher 10, DeepThroat outperforms both TBT and ProFlip on the efficiency trade-off. It achieves a higher successful rate using only 5 hardware iterations compared to other frameworks. And next, I'm going to show the ablation study. So trigger area percent we introduced before is that how much area we need to stamp on the original input figure we need. In DeepThroat, the trigger is a little square placed at the bottom right corner of the input figure. So the tab controls what percentage of the total area that patch occupies. And I introduced before, the larger stamps, the more efficiency we attack the module. So Finally, in our function, we calculate that the tap equals 14.06% as a default for Cypher 10 and Cypher 100 experiments is the best. And for ImageNet, tap equals 10.62% will be the perfect. And next, I'm going to introduce the row press versus row hammer. And I think it is introduced before by the ETH group, and we have a background knowledge about how row press works. And now I'm going to show the results. We use the row press instead of row hammer on the same chip Samsung DDR4. So before attacking, we provide the whole locations of the cells and to see what happens between the row hammer and row press. So this slide shows that the actual bit cells vulnerabilities map of a Samsung DDR4 16GB chip. And the empty one is the cells with no vulnerability. Orange one means it's only affected by the row hammer. The purple one means it's only affected by the row press, and the red one means it's affected both by row hammer and the row press. So we can see that the critical sufficient is set less than 5/1000 overlap in both row hammer and the row press. Which means the targeting the row hammer completely blind to the purple ones. Row press open a new attack surface instead of existing row hammer. So the attacker run I want to introduce how we run the attack. The attacker runs in 3 phases. Phase 1 profiles the entire DRAM chip to build the row hammer count, row press count vulnerability maps. Phase 2 limits the bit flip search to only those with bit flip physically located on vulnerable cells. This is a profile-aware constraint that makes the attack more efficiency. So the phase 3 executes the extra bit flips in inner layer search and finds the highest gradient bits. And then we run the row press again instead of the row hammer to see what happens. And this makes the result more visible. We can see that we start from the 100K row hammer to 900K row hammer. To make it more fair, we convert the row hammer count to the equivalent open time for the row press. So on the right side, we can see that 100 million cycles at 2400 millihertz equals 41.67 milliseconds. And this is almost equals 885 row hammer counts. So we can see that at the same time or same point, the row press will generate 20 times more bit flips than the row hammer. And what will happen if we run the row press on row hammer instead of row hammer on the DRAM modules? So this table measures that how many bit flips each attack requires to degrade a module's accuracy. So compared with the row hammer, we can see that row hammer needs average 3.6 times more bit flips to fully deplete a module's intelligence. So which means the key takeaway is that row press is not only faster at inducing bit flips in hardware, but also more efficiency to find the bit flips that's vulnerable in DRAM to decrease the intelligence. And these 4 curves visualize how module accuracy drops as the number of bit flips increase under each attack. Across different architecture and data modules, the steeper slope of the row press curve reflected that the efficiency and the number of the vulnerable cells. And we can say that existing defense doesn't work. So let's see the first three mechanisms. Once they achieve the none because all they operated at the training time, but deep charge we introduced before, they do not access to the training stage. They bypassed it, and all the defense mechanism doesn't work. And the clip doesn't work because it cannot detect it. They need to detect the error when the occurrence drops to 30%, while the ASR in deep charge only 1/10,000 is detected. So clip is not good for the deep charge. And also target row refreshment and memory activation count cannot detect the row press because row press have extremely few number of activation to generate enough bit flips to DNN. And finally, the ECC memory is also lose because the row press generate efficient bit flips for ECC to correct. And what we need to do in the future work is that we try to implement the row press instead of row hammer in deep charge to see what will happen. The two papers have a big overlap is that we use the DRAM Bender to inject the hardware fault into the DNN. And we skip the conclusion, and the more details can be found on the website. And every tutorial is the tutorial of the DRAM Bender is very good, and you guys can step by step follow it to implement our work. And open research questions is allowed because we still have a lot of directions to explore it in the future. And thank you. Any questions are welcome to be discussed.
What methods would a hacker have of looking page table memory so that they would know like where to execute the WordPress attack?
Makes sense. So the attack we assume that is the inner side of the DNN or something or somebody else. So they have the information about the weight information at the very beginning. They are we assume that the attacker is an employment or something, employer or other body who has the full knowledge about the DNN he want to attack. Yes.
You mentioned some of the new defense mechanisms that could mitigate these intelligence degradation attacks. Wondering if you can elaborate on any of the maybe any defenses that are different from those that can mitigate row hammer or row press completely at hardware levels. Do you propose or have you investigated any other sort of defense mechanisms tailored for this application space?
Yes, good question. So I don't think we have a general defense mechanism can cover both the row press and row hammer attack because of they have two different directions. The row hammer has a high frequent activating to make the charge leakage, but the row press only few activation, but prolong the time or the window to reduce it. So existing defense mechanism focus on different specific attack, modules. So if we want to combine them together, we need a more comprehensive or think more about how to take care both the two, I mean, disadvantages or directions. Yes.
Just building on that, follow-up question is, can you train the neural networks in a different way? Or can you make them aware of sort of post-training row ham and row press errors, like in their locations, and then make it more robust to these sort of attacks?
Yes, good question. So this question is now take account to our latest paper now. So our collaborator also have a how to say that mechanism, attack mechanisms that can bypass the training. So say make it realistic that no matter what inputs that you considered, you take the, I mean, polluted or poisoning data into training, you still got I mean, how to say that? You cannot totally ignore the bit flips effect in the last result. And we still can only change the stamps on the input figures. We can bypass your training. Yes. Yeah. Thank you.
Thank you very much. Do we have any other questions from the audience? Last call. Okay. That brings us to the end of the first part, I think. So we will go for a coffee break and meet you again at 4 p.m. Thank you for joining the first part of the DRAM Bender workshop.
Hi.
On my PhD work and
Yeah. Exciting.
But I'm using a different kit. It's different FPGA.
What is that? Which one is that?
I'm using a microchip.
Okay. Do they have support for DDR4 or HBM2?
They don't.
Oh, okay.
So what I have is I have a simulator memory on that in the sense of like an actual array, but not the FPGA itself. They have a DDR3.
Yeah.
So I'm looking for any other hardware where I can, experiment. So on DDR3, I'm able to do the simulation.
Yeah.
But I want to explore, extend my capabilities. So what should I do? What should I order?
So is this microchip? Because I don't know. But who develops it? Is it the Xilinx FPGA in there, or is it?
It is microchip.
Microchip is the FPGA developer. Okay. The way we
it used to be active before. I mean, I worked with microchip, so I kind of know how it works. So I just bought it.
I see. I have not heard of that company. You didn't say Altera, right? You said something else.
Yeah, it active. It has to be active.
Oh, I heard of that. But yeah, the way that or Xilinx makes it easy for us to do this sort of stuff because they provide us with an IP, basically IP port that.
I also worked for Xilinx, but how do you productize your version of the implementation, or it's just you buy the people who you help do the DRAM Bender, they bought their own hardware?
Exactly. They buy the FPGA board and
so
they download the repo and that's it.
Okay, so you can program by now.
Yeah. If you have if you have any of the boards for support, you can just download the repo and start working.
Oh, okay. Yeah. And you have a specific DRAM module, right?
You can test many different DRAM modules.
Okay, so do I need to, if I have to test different DRAM modules, so I have to try all those
DDR
modules?
Yeah. The U200 comes with four modules attached. But it's very expensive, right? So the DDR4 modules themselves cost almost nothing compared to the FPGA board's price. So, I mean, we find it reasonable to buy many DRAM modules to test them because they're relatively cheap.
Beyond DRAM, because you're working on DRAM. I also want to extend how we can do it for a DRAM or an SRAM or any other.
Yeah.
any
Those
solutions.
ones don't really, well, the other sort of new technologies don't have a standardized interface yet. That's like DDR or anything, right? So it's hard to find FPGAs that support them to begin with. I guess if you testing SRAM is different. I guess it's everywhere, but MRAM and other stuff, I don't even know how we would get to start building a test setup for those.
Yeah, but would your setup help in any ways to build any newer RAM? Like RAM is something I'm interested in.
I think we would have to look at the interface they provide. Is it more like the SRAM chips, where more simple, like, or is it more like DDR? If it's closer to DDR with all sorts of commands and timing parameters, then DRAM Bender can certainly help. You can reuse most of the hardware, maybe only change the physical interface part. And you would need to add a new adapter. But the rest you could keep. Like at least you can rely on the software and PCI transfers, all those other stuff.
You also tried implementing any LLM for the board.
LLMs? No, not really. We haven't tested it with any real application because the setup is not very good for testing applications. If you wanna, first you will need to extract all the memory requests or memory access stream from that word code, because the way DRAM Bender is programmed is you need to send, deactivate, recharge all these commands one by one, right? And it's also gonna, although it's fast relatively, it's still 600 million transfers per second, which is a very low bandwidth if you consider all these fancy HBM3 chips now. So any sort of evaluation you do in terms of performance, energy will need to be scaled somehow.
Thermal characterization.
Thermal characterization.
presentation on data to
Hello, is this good? Okay. Yes, we are waiting for a few minutes and I will shortly start. Okay, welcome back. In this part of the workshop tutorial, we will be mostly talking about Ramulator, although the invited speaker will mention DRAM Bender and more works about it. I will start with a brief introduction to Ramulator. First, maybe you've missed the beginning. Let me introduce myself again. I'm Nisa. I'm a PhD student at Software Research Group at ETH Zurich. I'm mostly interested in computer architecture, more so in memory system performance and robustness. And during this research projects, I have mostly used Ramulator, and I'm one of the major maintainers currently in the group. So I will first describe the first version of Ramulator, which was published in IEEE Cal in 2015. The paper was titled Ramulator, a fast and extensible DRAM simulator. So the motivation behind developing Ramulator was that DRAM and memory controller landscape was changing. There were many new and upcoming standards. Some of them are listed in here. And there were many new controller designs that we wanted to test, and we wanted to evaluate the performance and so on. And basically, to do these studies, we needed a fast and easy to extend simulator to basically quickly evaluate these systems and memory systems. So we developed Ramulator as a modular and extensible to different standards. It provided out-of-the-box support for many DRAM standards, from DDR3, DDR4, to emerging memory technologies like PCM and STT-RAM. And it also provided support for new proposals like row column, processing in memory operations, or subarray level parallelism, and so on. And at the time of the publication, it was faster than the fastest open source memory simulator, and you can see the results here. What's more important is that it enabled unique case studies. So one of the case studies that we wanted to highlight here was the comparison of DRAM standards. Here you see on the top part, in the table part, a lot of different DRAM standards from, again, DDR3, DDR4, to HBM, or LPDDR4, and so on. And all of these DRAM standards, they basically had different characteristics. So we wanted to evaluate them across many workloads and see what are the benefits of having one in our system. So on the bottom part, you see this performance comparison of DRAM standards compared to DDR3. And we basically were able to get insights about what to use in our system, what sort of trade-offs there are. And this was basically not possible to do before we developed Ramulator. So this was one of the unique test cases or use cases of Ramulator. And Ramulator was published in Cal again, and it is also free and open source, and you can still use it, still access it from this link here. And there are also steps to reproduce our results from the paper, and you can follow them to get started and get some results. And it is also possible to integrate it with other simulators like Jam5, which we had some instructions about it in the report. Ramulator enabled many works, and it was used by many people, like many groups, many practitioners from the industry and academia, and you can see a lot of the works cited it. And it was also loved by many people, and it was also loved by us, so we wanted to create a new version to make it more modern, to keep it modular and extensible, and support different case studies with it. So we developed a new version, Ramulator 2.0, and the paper that we described it was published in IEEE Cal in 2024. So the motivation behind it is still the same. So we wanted to, we saw a lot of changes in the DRAM and memory control landscape. We wanted to investigate robustness issues in DRAM. We wanted to test different aspects of data retention, read disturbance like row hammer, row press, column disturb, and so on. And we also wanted to test like performance issues related to memory systems. So we wanted to test processing in memory architectures, emerging memory technologies, like again, PCM and so on. And we wanted to also look into performance overhead analysis of read disturbance mitigation techniques, combining these two different things that are happening in the landscape again. So DRAM simulation infrastructures were needed, are still needed to understand, characterize, and evaluate the robustness and performance of DRAM. And we developed Ramulator 2.0, a modern, modular, and extensible DRAM and memory system simulator. Ramulator 2 models a wide range of DRAM standards and memory controller functionalities. It is modular and extensible. It has a modular and extensible software architecture, and it models DRAM operation in a fine-grained manner, meaning that it's cycle level accurate. And it is also used in many works since it was made online. So, okay, I will highlight some design features of Ramulator 2, starting with key design concepts. So we talked about modular and extensible software architecture. I will explain what I mean by that. All components in the memory system are modeled with two main concepts. So we introduced interfaces. An example of interfaces is the front end, and another one is the memory controller. Basically, this interface defines how these two components communicate. Like the front end sends some memory requests to the memory controller side, and the memory controller side sends some feedback after receiving the request and executing it. And the second main concept is the implementation part, where we implement these interfaces with different designs. For example, we implement the front end with a simple or out-of-order core model, and we implement a memory controller based on a generic DRAM controller design. And what we have here is that since the interface defines the communication, we can have different implementations without changing how they communicate. So an example I will give is basically this, like when we talk about like interfaces, the memory controller can include a lot of different components like address mapper, request scheduler, refresh manager, and role policy. And our system looks something similar to this. Here you see some general interfaces, like from the front end to the DRAM device to other components of the controller, like the refresh manager and so on. So what we did is we defined how these components communicated, and this is like an overall look into how the workflow is. I will not go into too much detail, but I think these are easy to explain, and if you ask questions, I would be happy to discuss. So what we wanted to have is that here, the interfaces are defining the communication, but the implementation can be changed. So each component that you see here can be flexibly changed without hard coding the other parts. Let's say that I want to have a different refresh manager. I don't need to change any other part of the controller, and I can just plug in my own refresh manager and keep the system the same. And this makes a lot of things easier when you evaluate different memory system designs. One of the things that this helped us is that we introduced memory controller plugins. This is like the highlighted part where we have the DRAM controller and the plugin part. And you can see that, again, the communication is defined. We made the key observation that many controller functions and utilities are triggered and updated by the currently scheduled command, meaning that the DRAM decides to issue one command, and many of these optimizations that we have in the memory systems just focus on that command being scheduled, right? So this helps us. The memory controller plugins are built with this key observation. And when we take this currently scheduled command, we can do a lot of things with like validation, with access pattern profiling. We can keep track of what's being accessed in DRAM and so on. And we can also implement a lot of row hammer mitigations. I will go into a bit more detail about the plugins with row hammer mitigations, which is one of the best use cases that we will highlight today. So this is how the DRAM controller interface communicates with the DRAM device model. It sends some DRAM commands. So we implemented the plugin interface, and we we added the interface and we implemented different implementations for this plugin. Here you see different ROHM mitigation techniques. All of them take the currently issued DRAM command, and they can keep track of these issued commands within their implementation. Basically, all of these implementations have different and design-specific tracking methods or probabilistic schemes to perform preventive actions. So here, for example, Power can decide when to probabilistically refresh victim rows and can send the refreshes through the same communication channel to the DRAM controller interface. And when we change the plugin to have a deterministic tracker like graphene, the communication stays the same, but inside the implementation, now we have more counters, activation counters, and we are basically counting each activation command that is being scheduled. And in contrast, in the probabilistic case, we are just basically getting a random number within the implementation. So this makes it very easy to implement a new ROHM mitigation, such that you just implement your own DRAM mitigation that you have in mind, and you don't need to change any part in the controller interface or other parts of the memory system. So I want to move on to the DRAM device interface. So we actually model the DRAM device as well, and we support implementations of many memory standards. Again, DDR3, DDR4, we added DDR5, and we have HBM, HBM to HBM3, and LPDDR5. And we are interested in expanding even more, so if you're interested in that, we would be happy to get help on that matter. So what's important about this DRAM device implementation or modeling is that we have this hierarchical DRAM modeling where we implement each level of the DRAM organization as a node in this graph. So all of these nodes are basically connected to each other with their relationships. Like we have a channel, and within a channel we have different ranks, and all of these nodes, each of these nodes have one state. This state can have the current state of the node itself, like it can be open, close, activating, etc. Or we can keep track of timing constraints. We can basically see that this node will be available for a new command in X cycles and so on. And we can also hold store some data about energy and power, like this time spent in each state and the number of DRAM commands that are served. So these can be done forward to DRAM power model to get power and energy measurements. And these can be extended. If you're interested in different statistics, you can extend this and you can keep track at the organizational level that you want. So DRAM commands are implemented as lambda functions that hierarchically traverses this graph and updates the states of each node. And what we do is we first check the current states of the DRAM nodes, these nodes, to decode which DRAM command to issue. And then we apply state changes based on the command, and then we update the timing constraints and power metrics and so on. So all of these nodes get updated whenever we execute a command and so on. We use the template library of generalized DRAM command lambda functions, which allows us to reuse common parts of these commands. If they need a common functionality, we don't need to rewrite it, or we don't need to write different functions across all, like the whole code base. And here we have this example function that is titled require all banks closed. What it does is it's basically checking the states of each node to see if they're, like these are the bank nodes, and to see if they're closed already. And this function is used for most of the DRAM standards we have, and we don't need to write it again and potentially introduce some bugs whenever we need this functionality. So we can use this sort of reusable functions across the code base. So there are more details about how we model things, and some instructions about adding new DRAM specifications, or adding memory controller plugins or mitigations and so on. And we have some performance comparison with other DRAM simulators in the paper. But I would say that there are also like even more details in the user guide and the documentation that we have in our GitHub repo. So if you want to get started with Ramulator, or if you want to learn more about it, I would recommend you to go check it out. So we validated Ramulator 2 in two ways. First, we validated timing, and we basically compared Ramulator 2's DRAM command traces against Micron's DDR4 Verilog model. We did this for different access patterns like streaming and random. And we also varied the memory intensities to cover more cases. And we found no timing or state transition violations. After that, we further evaluated the memory latency and bandwidth behavior accuracy against real system behavior with the study called Clean Up the Mess, which will appear soon in ISPLOS this year, which I will talk about a bit more in detail in the second part of my talk. So we also talked about integrating Ramulator to different simulators, and Ramulator 2 is even easier to integrate with other things. We talked about the modular and extensible software architecture, partially because of this. Using this structure architecture, Ramulator 2 can be packed into a library, a memory system simulator library, and you can switch the front end to different core models from Gen 5 to ChampSim, and you can still have a detailed DRAM simulation in the memory side. So this helps us have easy integration into other simulators to support detailed memory system simulation. An example of this is an integration with Gen 5, which we used in one of our recent papers. Again, I will talk about this paper in research highlights a bit more. For this study, we combined a more detailed core model with Ramulator 2's detailed memory system simulation. And we investigated timing covered and side channels introduced by rowhammer defenses. I talked about rowhammer defense plugins, so we used many of them in the study. We demonstrated side and cover channels leveraging two latest industry solutions to rowhammer, and we evaluated defenses against leak hammer using this integration. Another integration that I will highlight is with Virtuoso. Professor Mutlu also mentioned Virtuoso, which is another simulator that is developed by our group. Basically, this integration enables simulation of virtual memory functionalities combined with detailed memory system simulation. This paper introducing Virtuoso was published in ASPLOS last year, and it also showcased that we can enable fast and accurate evaluation of the hardware and software components of the virtual memory system with low simulation time and memory overheads. So there was a first workshop of Virtuoso at Micro last year, and it included one use case for this integration with Ramulator. So this is how we integrate Ramulator with Virtuoso. Here you see the core model is again from Ramulator, and MMU model is coming from Ramulator. But we basically integrated with Virtuoso to have the simulation of page fault handler in this case. And there are more details about this use case of enabling swap space studies coming again, like the virtual memory side coming from Virtuoso. And you can follow our tutorial from my live stream over here. I think this link this is the link in the bottom, and it will take you to the exact time spot where we have the Ramulator case study. But if you cannot do that, there's another Virtuoso workshop tomorrow that is happening, and I think Andreas will be happy to explain more about this. Okay, there were even more integrations of Ramulator from the community. So this paper from ISCA last year used an integration of Ramulator with ChampSim, and again combined with a detailed core model with the detailed memory simulation side. And we also use similar things again for our studies that are looking similar to this one. It's also artifact evaluated in open source, and I think you can find it from the paper here. Now I will sort of conclude this part with impact, future work, and conclusion. So Ramulator 2 has already enabled many works. It was used by many. It is still being used by many research groups, and we will cover some of the research works today as well. And I guess one question is that what is next for Ramulator 2? So we have been working very heavily on unit test and regression test coverage. We wanted to verify the timing constraints for all DRAM standards that we have, and we wanted to also include more detailed memory controller modeling, adding HBM controllers, for example. We are interested in having more DRAM standards and emerging technologies, and we are working on those as well. And we are building better tools for debugging memory system simulation using Ramulator. And some of these changes are happening soon, or they are they have already happened, I guess. Some of these changes, we packed them into one branch called Ramulator 2.1, and it is now online, and you can access it from this link. It's currently not the main branch, but we are working on making it the main branch and maintaining it further. So what has changed in Ramulator 2.1? So this is a major overhaul of Ramulator 2 that fixes almost all bugs identified by the current GitHub issues and by our internal testing and usage. And it has a more comprehensive support for new DRAM and controller features, more comprehensive set of tests and validations. We significantly improved the ease of use, configuration, and extension. We made overall code quality improvements, and we also added more detailed documentation and a usage guide. So I have some more details about the bug fixes that we did, mostly about HBM or LPDDR5 timing. We added better support for new DRAM and controller features, starting with the HBM controller. We have a new LPDDR5 controller. And all of these you can check from our GitHub branch. Okay. We added more validations and tests of workflows, and you can test all of these again. And it is all automated, so you don't need to go into too much detail if you don't want to, and you can just test whatever you implement, and it's very easy. And we made some improvements for like configuration. We made it mostly focused on Python instead of C++, which is which makes it easier to add it to other like Jam5-like simulators as well. And yes, so these are like the major changes, but there are even more details in the repo, so I would suggest you to go check it out. We are currently working on a trace visualizer. So this will be an DRAM trace visualizer, which will be coming soon. So this is, here you see, I'm not sure if it's visible, but basically each DRAM command that is being issued, we see this on the screen, and we see where it's targeted. So it's very easy to see which level it goes, which bank it goes, which row it goes. And we can also check the timing constraint violations. So it's easy to check the correctness of Ramulator. And also it's easy to check if your workload is doing something that you are intending it to do. So we read the dump trace file to view it, or we view it live from running simulation, and we can inspect memory requests and DRAM commands easily. And it's very easy to use, it's very responsive, so even if you have a very long running simulation, it's easy to render it in the browser. This is not online yet, but we are testing and we are interested in making it online very soon. Okay, so Ramulator 2.1 is released on GitHub, and for now it's not the main branch again, but we are interested in doing so in the next few months, and we would be happy if you could check it out and let us know if you encounter any issues and if you have any suggestions for features and so. So I want to also talk about how to contribute to Ramulator 2. First part is easy, I guess. You use it, you report any issues, feedback you have on GitHub. We are interested in using GitHub discussions more and have lively discussions over there. And if you want to add new features and components or add more test cases, that would be also good. And you can check our detailed README and documentation to contribute to it. As a general call for contributions, again, like very interested in doing this mostly for Ramulator 2.1 as well, but also 2.0 is okay. We are interested in integration with other simulators. We are, again, we have some versions of ChampSim, Sniper, or your favorite system simulator. Maybe we have an integration, but we want to test them and we want to include steps to make it happen or make it easy for others in the README files as well. And again, we are interested in more DRAM standards, more DRAM timing presets, or if you want to add more functionality in the memory controller, we are also interested in making DRAM controllers or memory controllers smart and add more features. That would be also good. And of course, if you have other things in mind, we're also happy to support and help with all. So again, these are the paper and the GitHub, and we are happy to support and help anyone who wants to use it. So this concludes the first part of my talk. I would be happy to take any questions. Sorry.
It was a very nice presentation, very nice production for I was wondering, does Ramulator support DBFS mechanisms, or do you really need to support DBFS? Maybe you can just change the frequency at runtime.
So right now it's not supported. I think what we have is basically a support for getting the stats for DRAM power and so on, other tools to have like the trace of the commands that we are issuing or performing in the memory side. But it would be interesting to think about it and make it more like integrated with Ramulator. If you're interested in doing something like that, I think we would be happy to help and work together.
And the other thing is, have you changed the DBFS state?
Mm-hmm.
Some latency just to change the state.
Yeah. Those could be handled as like adding some commands or like timing constraints again with that support, with that like dynamic integration. I think those parts could be handled a bit easier. Maybe the states changes in like each node and so on. Maybe these are more tricky to handle. But I think it would be really interesting to do some studies with like different workloads and so on.
You mentioned about some future work about verification of the timing standards. I was wondering about like the existing timing restrictions within the DRAM standards, or is like, let's say I added a new DRAM command and to verify that it is like working well with the existing restrictions.
So I think both could be possible. What we have so far with the verification system is that we sort of verify if all the standards comply with JEDEC standards. But if you add some constraints and you have a good idea about how they would, how they should be implemented, with that like trace visualizer, for example, it would be very easy to find violations in that like behavior throughout execution and so on. Does that answer?
Yeah.
Okay. I don't think I don't think we're cross-validating. The part that we did this validation from Verilog sources from Micron, that's probably the most sort of close to what you described, as I understand. Other than that, right now we don't have that, but it would be still interesting to see like what other validation cases that we can get out of it, and yeah, I think that would be interesting, but currently we don't have.
On the topic of verification against Verilog products, was that more using kind of like no simulation like runtime, or was that more of like a generate the outputs from both runtime?
It was more similar to the other, like the second latter part. We basically validated the state transitions, the timings of DRAM commands after executing both, like in both platforms, let's say. Okay. I think that's all. Thank you for the questions. Let me switch to the other part. Your demo is still here. Is the live stream good?
Yes.
Okay. 1 second. So in the second part, I want to talk about some of the research that we have done so far using Ramulator 2 mainly. I will start with one of our latest papers on real system modeling accuracy of Ramulator 2. Again, this paper is titled Cleaning Up the Mess, Reevaluating the Real System Modeling Accuracy of Ramulator 2, and it will appear at ISPAS in the next month, I think. Yeah. So a recent work, the MES paper, aims to compare the accuracy of memory system simulators against real systems, and they included an evaluation of Ramulator 2 and DAMO, which is like DAMO is the integration of ZSIM and Ramulator's first version. And they also, for this comparison, they introduced this MES benchmark, which combines streaming and random access patterns, and they leverage latency bandwidth curves, which I will show in this figure. So here on the x-axis, we have used memory bandwidth, and on the y-axis, we have the memory access latency. So in real systems and memory system simulators, they measure the memory access latencies of this MES benchmark, combining the different access patterns. And they also calculate the used memory bandwidth. So in the end, we have this sort of curve that is showing the system behavior. So when we go to the highest point in this curve, we have, as we go to the highest point in this curve, we have increasing memory intensity. So this is this one curve is a combined result of many simulations and with increasing memory intensity. And they evaluated varying read and write intensities, and they basically created a lot of curves comparing different sort of like read-write intensity of a workload. So they evaluated real systems, and they showed these results. So this is one of the DDR5 systems that they evaluated. And these results are claimed by the MES paper, so the figure is coming from there. And they also evaluated different memory simulators like Ramulator 2, and these are the results that they claimed in the paper as well. As you can see, the two figures are not similar to each other. And they also conclude that Ramulator 2 poorly resembles the actual system performance based on these results. So we did our own analysis on the resources that they shared and paper. And what we ended up concluding is that Ramulator 2 simulation results in the MES paper are incorrect, and at the time of the publication of the paper, they were not reproducible. So we basically took the artifact. The paper was also artifact evaluated, and we tried to run Ramulator 2 tests as they described, and we were not able to get the results because first, Ramulator 2 source code was not there, and second, when they uploaded after our contact, we found like some more issues with the changes in Ramulator and with the evaluation methodology, which we described in the paper. So we also found out there were many fundamental configuration errors. I will describe that technical part more in this presentation, but if you're interested in the other parts, of course, you can check the paper. So we identified multiple errors in the configuration of Ramulator 2 in the MES paper, starting with basically the number of channels that each system had. So compared to the real system, Ramulator 2 had half the channels. And this was because they were extrapolating single-channel DDR5 results to 8-channel DDR5 instead of 16-channel DDR5 results. And again, these are the results, and we think that the fact that they achieved half the memory bandwidth is coming from the fact that the configuration had half the channels. The second configuration error was hard-coding the cache configurations to very low numbers like 0. And they also had an observation that Ramulator 2 results, basically that behavior coming from Ramulator 2 ended up with like memory access latency very low. And this was coming from the hard-coded cache configurations that they had. And again, this results in significantly smaller DRAM round-trip latency and significantly lower queuing delay, which results in significantly lower memory access latency. So we evaluated the MES benchmark. As described in the paper, we introduced minimal changes to the code. We just changed the front end to implement the benchmark better. And we configured Ramulator 2 correctly and evaluated the same access pattern described in the MES paper. And these are our results. Yes. So as you can see, when configured, correctly configured, Ramulator 2's simulated memory system performance resembles real system characteristics a lot more. And what we wanted to really show here is that basically the used memory bandwidth reaches where it's supposed to reach when given enough channels, the same channels as the real system. And the curves look very similar to what we have what they have showed in real system results. And our evaluation resources are open source, and you can access it from this link, and you can reproduce it using 2 scripts, and basically you can get the Ramulator 2 results with correct configurations. And after this, we were interested in testing other DRAM standards that we had in the repo. So we tested even more standards from DDR3, DDR4, DDR5, LPDDR5, and the results were similar. And we also tested our HBM standards, and these are the results coming from that. And the second part, like the other standards that are coming from Ramulator 2.1, but the underlying standards are the same. But we just added this like easy testing methodology coming from MES benchmark, or like our evaluation of the MES benchmark. The second part of the paper, we describe our analysis of the move evaluation in the MES paper. So they similarly evaluated a DDR4 system and compared it to Damu's memory system simulation. Again, Damu is an integration of ZSM and Ramulator. And as you can see here, I'm not sure if the second image is easy to see, but what they conclude is that ZSM and Ramulator, or Damu, resulted in a static memory access latency. And we basically analyzed everything again with the source codes and all. And our analysis showed that the move simulation results in the MES paper use wrong statistics, simulation statistics that are unrelated to simulated DRAM performance. And that's why it's showing a static memory access latency. And similarly, we evaluate the move, again, using their source codes for the benchmark. And these are our results. We conclude that when correct statistics are used, the move's memory access latency is not constant, in contrast to what the paper claims. There are more details in the paper about the evaluation and also about other issues that we have found with reproducibility, with other scholarship issues and so on. So you can check the paper. We will update it with the ASPLOS version soon. So the move results will be added later, possibly tomorrow. Okay, so in the paper, we also wanted to discuss some best practices for Ramulator 2 and the move, and possibly for general usage of open source simulators. So we recommend understanding the simulator that we are using better and not use it as an absolute black box, meaning that maybe we need to get familiar with the JEDEC standards, DRAM standards, like that would help with DDR5 channel issue. And it would be good to understand the memory organization and configurations which are documented in the code. Again, getting to know the simulator a bit more. And it would be good to also like understand the simulation methodology and simulator implementation sufficiently to use the correct statistics to end up with correct results coming from simulation. And apart from that, we also think that it's one of the best practices to communicate with simulator developers and user community of the simulators when unexpected results are observed. So this concludes this part about cleaning up the MES paper. And I will continue with the raw hammer mitigation evaluation research highlights. But before I do that, I would have to take any questions about this paper if you have. Cool. Okay, so starting with where we left off with the Ramulator paper. So we implemented many raw hammer mitigations in Ramulator 2 as a part of use cases for Ramulator 2 in the initial paper. And what we added was a cross-section performance overhead evaluation of different raw hammer mitigation techniques. We evaluated 6 different raw hammer mitigation techniques, all implemented as plugins to the same memory controller implementation. And this is like the results that we showed in the paper. So on the x-axis, we had the raw hammer threshold. And as DRAM becomes more vulnerable to raw hammer, we are going towards lower thresholds. And on the y-axis, we have the normalized weighted speed up. So here, what we concluded from these results was that as DRAM becomes more vulnerable to, well, the text is wrong, but as DRAM becomes more vulnerable to raw hammer, evaluated raw hammer mitigations incur higher performance overheads. after this paper, after like developing Ramulator 2, there were recent improvements in JEDEC in 2024. And what they introduced was parallel activation counters inside DRAM devices. So this was one of the major changes in the DRAM standard. So we wanted to evaluate it and see how it compares to other mitigation techniques. And we did this in this paper that was published in DRAM-sec. So we extended the memory controller implementation with support for parallel activation counters that is described as in the DRAM standard. And we also implemented the backoff signal that gives time to DRAM to perform preventive actions. And we compared this new mitigation industry solution, PRAC, against state-of-the-art mitigations. And these are the results that we showed in this paper. And the results show that PRAC introduces non-negligible performance overheads due to increased DRAM timing constraints. This is one of like the fundamental drawbacks of this mitigation that was identified in this first evaluation of PRAC in DRAM-sec. So this was very easy for us to do because we already had all these comparison points implemented, and we had the memory system like simulation already for just extending this with PRAC and evaluate it. So after this evaluation, we wanted to also address these drawbacks that we identified in PRAC. So again, another recent paper in HPCA. So we titled Chronos, Understanding and Securing the Cutting-Edge Industry Solutions to DRAM Disturbance. So we identified two major drawbacks of PRAC by extending our initial analysis that was published in the DRAM-sec paper. The first drawback is that we have increased critical DRAM timing parameters that are coming from PRAC, that are coming from the design of the PRAC. And this leads to large performance overheads, even at high read disturbance thresholds. And the second drawback is that PRAC is vulnerable to wave attack, where you do a row hammer attack in many DRAM rows. And this requires configuring PRAC with an aggressive row hammer threshold, meaning that we will have more performance overhead coming from this aggressive threshold setting. So this leads to poor scaling to low read disturbance thresholds. We propose Chronos, and the key ideas of Chronos are twofold. So first, we introduced concurrent updates of counters while serving DRAM accesses so that we don't need to wait for longer to update these activation counters. And this means that we don't need to increase this critical DRAM timing parameters. And second, we prevent wave attacks by providing DRAM chip more control over the backoffs that are the preventive actions that the DRAM can do, and preventive refreshes. So this leads to having better scaling to low read disturbance thresholds. We evaluated Chronos again with Ramulator 2, just extending what we had for PRAC, and we had this comprehensive evaluation across many workloads, and these are the results. And we conclude that Chronos reduces the performance and energy overheads of PRAC and outperforms the state-of-the-art solutions. So that's how we address drawbacks of PRAC in this study. Okay. So if you have any questions about this pipeline here that we had, I would be happy to take them. Otherwise, I will move on to a bit more different perspective. Okay. So the last work that I want to highlight is a recent paper using Gen 5 and Ramulator 2.0 integration, titled Understanding and Mitigating Cover Channel and Side Channel Vulnerabilities Introduced by Row Hammer Defenses, which was published in Micro last year. So I will talk about the motivation and the problem a bit more because we're sort of entering the security perspective. So modern computing systems are vulnerable to security attacks such as cover channel and side channel attacks, where an attacker uses the shared computing system to communicate with other attacker processes or to spy on other applications that are executing at the same time. So a set of these attacks exploit shared hardware structures that result in different execution time for executing a type of operation based on the input or the current state of the shared structures. So this means that timing differences lead to leaking information. Let's take a closer look at these computing systems. Here we have a typical DRAM-based system with a CPU and a DRAM module connected over an off-chip link called the DRAM channel. We already talked about read disturbance, and as you know, DRAM is vulnerable to read disturbance, where repeatedly opening and closing a DRAM row causes row bit flips in nearby DRAM cells. To make things even worse, read disturbance again is getting worse, and we see reductions in the minimum hammer count needed to induce a bit flip. This means that DRAM cells are becoming increasingly more vulnerable to read disturbance, and this requires having low-cost defenses. To enable such defenses, recently the R5 specifications introduced two new defense frameworks to mitigate row hammer bit flips. The first one is what we discussed so far, probe activation counters, or probe activation counting, or PRAC, which introduces these activation counters to accurately track aggressor rows activation counts inside the DRAM. And the second framework is called refresh management, or RFM, which introduces a command to provide DRAM with the time to perform preventive actions. The problem with this is that, like, the industry has already standardized multiple row hammer mitigations, yet their full security implications are not known. So this brings us to the question, do industrial and academic row hammer defenses introduce new covert and side channel vulnerabilities? And in this work, we show that the answer is unfortunately yes. We make the key observation that preventive actions have two fundamental features that enable covert and side channels. The first one is that these actions often result in high memory access latencies for regular memory requests. Again, we have our DRAM connected to the CPU. So these preventive actions usually have higher latencies, and this means that all other requests, when this DRAM is doing these preventive actions, all other requests need to wait for that action or preventive action to complete. So this means that they have higher memory access latencies. The second feature is that a user can leverage memory access patterns to intentionally trigger a preventive action, such that the user can construct requests targeting the same location in DRAM and practically hammering that DRAM row. And DRAM responds with doing preventive actions, which means that all other requests, again, experience higher memory access latencies. We introduced leak hammer, which is a new class of attacks that exploit row hammer defense-induced memory latency differences. The key idea of leak hammer is to first deterministically and intentionally impose observable latency overheads on requests with preventive actions. And second, accurately infer victim applications' memory access patterns that result in preventive actions by just observing the shared structures. We demonstrated three different attacks as the case studies of leak hammer. We first established PRAC and RFM-based covered communication channels. Then we demonstrated a website fingerprinting attack that leaks which website is accessed by a victim user by just observing the preventive actions that are happening in the system. I will talk more about the first case study, PRAC-based covered channel attack. So we covered probe activation counting. I will just go over it very quickly. PRAC introduces activation counters that accurately tracks activation counts of each row. And whenever we have an activation to one row, this results in incrementing the counter that corresponds to that row. So after a while, as these activations accumulate, we reach a threshold called the backoff threshold. This means that now the victim rows that are close to this row require preventive actions. And we identify this row as an aggressor row. And the DRAM module sends a backoff signal to the CPU side saying that I need some time to perform like preventive refreshes or perform some preventive actions. And after receiving the signal, the memory controller sends an RFM command, which provides a fixed time for preventive refreshes to happen. So in this time window, DRAM becomes unavailable and performs preventive actions, refreshes. And after that, DRAM becomes available again, and the controller can send more activations to or other commands to DRAM. In order to exploit this for an attack, we need to first verify if we can observe these PRAC-induced latencies. So we test if an application can intentionally trigger a PRAC backoff and observe PRAC-induced higher memory access latencies. We construct the routine to trigger this, activate two rows, and increment their counters in the same bank. And we basically construct this routine and record the memory access latencies. And these are the results. So on the x-axis here, we see the memory requests, and on the y-axis, we see the memory request latencies. And these are the latencies that this routine records. So what I want to highlight here is that These request latency latency values are can be categorized into 3 classes. First, we have track backoffs as the highest latency that we see based on the standard values. And next, we have periodic refreshes. Again, it's a high latency, but it's not as high as backoffs. And other than that, we have row buffer conflicts, or even lower, we could have row buffer hits, but we don't have in this case. So we conclude that we can observe backoff latencies as the highest peaks in this figure. And these values are consistent with the specification and can be distinguished from regular memory operations. Now, I will go over the attack overview quickly. Here we have a sender and a victim, a sender and a receiver, and they want to communicate, they want to send this message to the receiver side. They only share the DRAM device, so they collocate their rows in the same DRAM bank, but they don't share actual data. And they agree on some transmission windows saying that we will transmit 1 bit in this time window, and only 1 bit will be transmitted at this time. They also agree on an encoding saying that logic 1 value will be transmitted with a backoff, and the logic 0 value will be transmitted with no backoff. And after that, they can start the attack. So to receive the message, the receiver executes 1 loop where it accesses its own DRAM row and measures the time it takes to access it. And after each transmission window, this results in having a trace of latencies that can be used to determine the bit value. To send the logic 1 value, the sender needs to cause a backoff happening in the system. And to do so, the sender also accesses its own DRAM row, and since these DRAM rows are in the same bank, this results in activating both rows and incrementing their activation counter. And after a while, the DRAM module sends a backoff signal, and at that point, the receiver measures a high memory request latency, and then they can detect this as a backoff and can determine the bit value. To send a logic 0 value, the sender needs to cause no backoffs, so throughout the transmission window, the sender just sleeps. And since the receiver is active on its own, the activation counter is not increased as much. And at the end of the transmission window, the receiver measures something like this and can determine no backoff has happened in this transmission window, and then determine the bit value. So they repeat this until the whole message is sent. We validate this proof of concept by transmitting a 40-bit message. And here on the x-axis, we see the transmission windows. And on the y-axis, we have the number of backoffs detected by the receiver, and these are the results. So the background color here is the bit values that the sender intended. And as you can see, when the sender wants to send a logic 0 value, the receiver receives no backoff, and vice versa in the other case. So we conclude that the receiver successfully decodes the sender's message, and we also evaluate the attack throughput, and we basically calculate the raw bit rate as 39 kilobits per second. We then look into more noise analysis because sender and receiver are probably not alone in the system. So we look into the impact of having some other applications running in the background or some noise intensities coming from micro benchmarks. And we conclude that this covered channel attack maintains its capacity until a very high noise intensity value. For the second covered channel attack, we did something similar with another industry solution called RFM. I will not go into too much detail, but the conclusion is that we can also exploit it to create a similar attack. And you can find more details in this in the paper. Now, I will again cover the website fingerprinting attack quickly because I'm running out of time. So in this attack vector, we have the attacker and the victim. And the victim loads a website using a web browser. And the attacker wants to determine which website is loaded just by observing their own memory access latencies. They share the DRAM module, but they don't need to collocate in the same bank or anything because due to the changes in the standard, this backoff or preventive actions affect the whole DRAM module. So in order to do this attack, the attacker first needs to figure out how to fingerprint. So the attacker starts by measuring memory request latencies across different rows, accessing different parts of the memory, and measures access latencies to detect backoffs during like one website is loaded by a browser. And by doing so, the attacker can create fingerprints using backoffs of this whole load execution. And this is like what one fingerprint looks like. Each line here corresponds to one backoff that is happening in the system. And yeah, basically the attacker can collect many of these fingerprints from different websites, many instances of the same website, and so on to create a database of fingerprints. And after that, we can launch the attack. So the victim loads a website, and at the same time, the attacker gets the fingerprint of this execution time. And then the attacker compares this fingerprint to the database that it created in the first preparation step. And after that, the attacker can determine the website. So we evaluated this proof of concept attack again across 40 most visited websites by collecting backup fingerprints, only the backup fingerprints, nothing else. And we basically used a machine learning approach to classify the websites that we tested. And we only use simple and lightweight machine learning models to see if it's possible to classify them, but probably more complex models would give better accuracy results. But our evaluation showed that using backoff-based fingerprints, we can classify websites with up to 75% accuracy. So this shows that this is a promising approach, and backups can be used potentially to do this attack in real systems, perhaps one day. Okay, so we discussed how to mitigate leak hammer next, which again, I will not go into too much detail. We proposed 3 countermeasures, from eliminating the timing channel completely to reducing the channel capacity with less performance overhead, to limiting the attack scope to existing attacks. And we evaluated all of them across many workloads. And our conclusion is that mitigating our solution that mitigates leak hammer, which is fixed rate IFM, is more costly when we go to more vulnerable DRAM devices. So as the raw hammer threshold decreases, the performance overhead increases. And at those levels, if your system is too vulnerable to raw hammer, maybe it's a trade-off to consider to have a mitigation that doesn't eliminate the timing channel altogether, but it limits the attack scope, or it reduces channel capacity to make the attack less practical. There are more details in the paper, and you can check it out from this link. And leak hammer is also open source and artifact evaluated, and you can check it from this link. And that concludes this part of the talk. I would be happy to take any questions.
So that presentation as well was really nice knowing about the leak hammer. So my question is about the website fingerprinting. So, for instance, for YouTube, you can run videos for sure. Videos can run resolutions with. I can also do some commenting, so I can do different kind of stuff. Does it work for all of them, or does it have to match with the fingerprinting that you have originally?
So we tested this like all websites with their homepage, let's say. So the content changed over time because we were like doing this, getting these fingerprints through some time window, right? The content changed. We did not run like play videos, for example, for YouTube. But for example, we tested with Reddit, which could have some videos auto-playing in the background, or it could have some text-based posts and so on. We didn't see a big impact of this, but we did not also intentionally try with different videos for YouTube, for example. So we didn't change the content. We just loaded the homepage and the fingerprints. They were different at times. So I would say that maybe it depends on like what sort of thing is running in the background on that homepage. But we didn't see that it hurt the accuracy, as to say.
So does it have any effect on the browser part?
Yes. That's a very good question. The memory intensity of different browsers are apparently different. That's one of the observations that we had from this sort of evaluation. I tried with different browsers and ended up using the one that has the highest memory, usage to make the study a bit easier, let's say. But the other browsers also showed like good accuracy results with like fewer. We would potentially need to test with websites that would create a lot of requests. But in the end, we were able to classify some websites still, regardless of the browser.
So I'm interested in like the portability of the fingerprints obtained on one system. So like instead of the attacker having to curate the like the data set of the fingerprints on the same system that the victim is running on. So is it possible for like maybe like crowdsourcing like sort of like a data set curation where like those fingerprints using black box are collected from different systems, and then the attacker can like infer the website based on this like global data set instead of relying on being able to always like at least like assuming that the attacker is always like located with the victim on the same system.
So that's again a good question. That's also what we considered at some point. A part of the study, as a part of the study, we did this on one system. So all the fingerprints were coming from the same system from different times, but different like internet connectivity and so on. But I think it would be interesting to see if we could crowdsource, like you said, like if we were to get these fingerprints across different devices. I would expect some behavior would be similar based on like the content of the page and so on, because like the insights that I did not go into too much detail, for example, text-based websites had similar behavior. I don't expect that memory access behavior to change with different devices necessarily, but maybe like one question that I had was if I'm connected to the same, like if I'm connected to internet from a part of the country and compared to another country, for example, would it change because you would be accessing different servers potentially? So those are things that we could not control as much, but I think it would be interesting to see different devices, maybe location. Maybe it's also easy to or possible to understand where you're accessing the data from or something.
Great, yeah, just one follow-up. So like I'm asking this question because you said like different browsers have different access patterns, which is like reasonable, logical. But I think like if the data set is curated from the same browser, maybe even the same version, but across multiple systems, like at least my intuition says that like they wouldn't be so different from like generating from one system to the other. Yeah, so that would be really interesting to analyze. Yeah, thank you.
Yeah, thank you.
Any other questions?
Can you do this? Yes. Let me see. Ataberk, can you help me?
Yes.
I had the slide here. Okay. Yes, this is correct, right? Okay. If you want to use the pointer, you can also do so here.
Okay.
Okay. Our next speaker is Haocong. He's a PhD candidate at Seoul National University, advised by Professor Junho Ahn. His research interests include memory systems, DRAM microarchitecture, memory reliability and security, and LLMs. And he's going to talk about very experienced with Ramulator and DRAM. Thank you. Thank you. My name is Haocong, and I'm, the PhD student at Seoul National University, was advised by Professor Jung Wan. And in this talk, I'll share our experience with two infrastructures that have been very useful for our research, the Ramulator and DRAM Bender. So I'll focus on two case studies from our lab, DRAM scope and ROM. Before the case studies, I want to briefly note that these infrastructures have been useful to our lab across multiple projects. I'd like to thank to the Ataberk group for open sourcing the Ramulator and DRAM Bender. We've used the Ramulator in architecture studies and DRAM Bender or soft MC in DRAM characterization and reliability studies. Among these projects, today I will focus on two examples. The rest of the talk is organized as follows. First, I'll present DRAM scope as a DRAM Bender case study. Then I'll present ROM as a Ramulator case study. Finally, I will close with a few takeaways. Let me begin with our first paper, DRAM scope uncovering DRAM microarchitecture and characteristics by issuing memory commands. Let me give you a brief overview of the paper. We analyzed the structure and error characteristics of DRAM. Through macroscopic analysis, we characterized the DRAM structure, and through microscopic analysis, we identified bit-level pairs. First, let's look at the DRAM organization from a macroscopic perspective. DRAM has a hierarchical structure, and each DRAM cell consists of one access transistor and one capacitor. Modern chips are also used on open bit line structure, where cells connected to sense amplifiers above or below. However, if you look at this from the microscopic perspective, we can discover new insights. Here's the microscopic view of DRAM. Modern DRAM cells adapt to 6F square cell structure. If we zoom in, we can see that when the buried water line turns on, it connects the bit line and the cell's capacitor. On either side of water line 1, there is water line 0, which shares the same piece of substrate, and water line 2, which does not. We call this the neighboring gate and passing gate, respectively. To characterize the DRAM structure and properties, we use three techniques: activating the bit flips, in-DRAM row copy, and retention time test. Using these techniques, we can characterize DRAM chips non-destructively. All three techniques were implemented and executed using DRAM Bender. The first technique is activating induced bit flips. This happens when activating a row flips the data in adjacent rows. There are two attack methods, row hammer and row press. Row hammer involves many short activations, while row press involves fewer but longer activations. The second technique is in-DRAM row copy. Row copy copies data from the one row to another row within the same subarray. The process involves activating the source row to latch the data in the sense amplifiers and then copying it to the destination row. The third technique is the retention time test. A DRAM cell in charged state loses charge over time. We use this to distinguish between the true cells and anti-cells. Here is our testing platform of DRAM Bender. We conducted experiments using DDR4 and HBM2. We also controlled the DRAM chip's temperature with temperature controller and lower heater. We tested lots of DDR4 and HBM2. Before diving into the analysis, let me highlight the common pitfalls found in prior work. There are address and data remapping schemes. Some of this information is disclosed, but it's easy to overlook. First, the address can be remapped at the R3 chip. Because of the R3 chips, some chips receive on data with certain bits inverted. Second, the row address can also be remapped internally within the chip. Many prior studies have identified this using single-sided row hammer attack. Finally, the DQ pins between the DIMM and each chip are twisted. This figure shows an example of how the twists occur. Additionally, the data is twisted differently for each chip. By accounting for these pitfalls, we are able to conduct accurate experiments and analysis of DRAM chips. Let's start with a macroscopic analysis. We conducted multiple analysis on DRAM microarchitecture. Here are three representative ones: data swizzling and math structure, coupled row activation, and subarray substructure. Data isn't stored sequentially in the DRAM chip. Instead, it's internally swizzled and reorganized. We call this DRAM swizzling, and we reverse engineering it. First, we identify the cell adjacency. The error rate of row hammer attack varies with data parents, indicating that cells influence each other not only vertically, but also horizontally. In this figure, the yellow cell is the victim cell. And we identify the influencing cells by varying the data parent. Second, we used row copy to distinguish the odd and even bit line. By observing which subarray influences a given cell, we can determine whether its bitline index is odd or even. In short, we identified the data swizzling using row hammer and row copy. By using cell adjacency, we can also find the width of the map. Just like there are sense amplifiers between the subarrays, there's water drivers between maps. Therefore, we believe there is no row hammer effect between maps. We measure the map width as 512 bits and 1024 bits. So inside your chip, data is remet by data swizzling, and the map widths are either 512 bits or 1024 bits. Next, we found coupled row activation. This is when two physical row addresses access rows on the same order. Normally, only one row corresponding to the input row address is activated. But in certain bifault chips and HBM2, we noticed another row being activated as well. We found that the gap between these coupled rows is half of the total row count. So for DRAM chips, activating a row can unintentionally activate its coupled row. Finally, we did a subarray level analysis. Most subarrays are sequentially adjacent following the row address order. However, we found that some subarrays affect each other even if they have a large row address difference, such as a quarter of total rows. These are called edge subarrays, and the two edge subarrays work together like a single subarray. The two edge subarrays work in tandem to form a single full subarray. Now let's take a microscopic view of DRAM. We focus on two main topics: 6F-square induced activating this flip characteristics and the adversary data parent for the minimum hammer count and bit array. First, let's understand the 6F-square cell structure a bit more. In a single row, the cells alternate between the top and bottom of the quadrant. This means the cells of a single row alternate have a passing gate and a neighboring gate relationship with the adjacent quadrant. Importantly, the bitline mechanisms differ for each gate type. Each gate's cross-sections looks like this. And when activating a neighboring gate, electrons gathered by channel inversion are injected into the victim cell, causing a bit flip. On the other hand, when the passing gate is activated, high voltage attracts electrons from the victim cell. When the row is precharged, the electrons spread out, resulting in a bit flip. We also need to consider whether the water index is odd or even. In this figure, you can see that the arrangement of cells in the row is identical when both water indexes are odd. However, when comparing odd and even indexes, the cell arrangements appear different. So we consider whether the water index is even or odd. Here are our attack pattern of activating these bit flips. We conducted single-sided attacks for both row hammer and row press attacks. This figure shows the average bit error rate aggregate by bit index modulo 32 for victim rows with even water indexes. First, with row press, B flips were only observed in victim data 1, as reported in the row press paper. Furthermore, in data 1, B flips occur in both odd and even bits. Unlike row press, row hammer causes B flips both data 0 and data 1. However, there's a pattern. In figure E, when the data is 0 and attacked by the upper aggressor row, B flips occur only in odd bit cells. Conversely, in figure F, when the data is 1 and attacked by the upper aggressor row, B flips occur only in even bit cells. If the aggressor is changed from the upper to lower, the pattern reverses. Let me summarize these observations. From the row press attack, B flips occurred only in data 1 and in both gate types. From the row hammer attack, B flips were observed in both data 0 and data 1. But in data 0, B flips happened in only one gate type, while in data 1, they happened in the other gate type. So we can classify the B flip parents not only by data and attack method, but also by gate type. Now let's look at the adversary data parent in terms of the minimum activation count. We found that when the cells surrounding the victim cells have opposite data to the victim cell, the hammer count is lowest. Also, we tested the adversary data parent for a bit array. As a baseline, we set all cells in the victim row to either 0 or 1, with the aggressor row holding the opposite values. We found that the worst case is when the victim and aggressor rows hold 3, 3, or CC. Data is most vulnerable when it alternates at 2 cell intervals, not 1 as previously thought. So when all near cells from the victim cell hold opposite value, the victim cell becomes most vulnerable. And the bit array can increase by up to 1.69 times in the worst case data parent. If you want more details, please refer to the paper. And next, I'll present from row-grained access memory system for large language models as a Ramulator case study. As we all know, large language models have seen exponential growth over the past few years, with model sizes now reaching the terabyte scale. To generate token with the low latency and low energy, many companies are competing to build their own custom AI chips. Let's first look at how LLM computation works. LLM inference consists of 2 stages, prefill and decode. Both stages use the same computation structure, but prefill takes all input tokens at once, while decode processes 1 token generated from the previous step. Each stage consists of tens of decoder blocks, which are composed of 2 main parts, self-attention and feedforward networks. Most of the computation is based on GEM and GEMV operations. In the prefill stage, most operations are GEM because multiple input tokens are processed simultaneously. Even with large batch sizes, the computation still behaves as GEM. In the decode stage, since only 1 token is given as input, most operations appear as GEMV. However, when a batch size is large, the number of GEMV's operations increases and they often behave like GEM. Now let's look at how much data is accessed in each operation. This box plot shows the distribution of vector and metric sizes accessed when the batch size is 1 and the sequence length is 2K. All accesses exceed kilobytes and are often close to the gigabytes. With the large batch sizes used in a modern system, many vectors are accessed simultaneously. So the question is, how are these large vectors and matrices stored in memory channels? To answer this, we first need to understand the HBM, which is widely used in Olgun AI accelerators. HBM uses thousands of IOs and 3D stacked DRAM to provide high bandwidth, while preserving 32-byte cache line granularity. Let's assume this vector and matrices are stored in HBM. They are split into many 32-byte chunks and are distributed across all channels to maximize bandwidth. As a result, kilobyte or megabyte sized vectors and matrices are split into hundreds or even millions of small pieces. However, LLM access data at least in kilobyte units and often used large batches. Do we really need to keep such a fine-grained 32-byte accesses? To understand why current systems are designed this way, let's look at conventional memory system work. DRAM has evolved by increasing I/O frequency, but the entire DRAM core frequency has remained nearly constant. To bridge the gap, features such as bank groups and pseudo channels were introduced, and channel width was reduced. All of these techniques share a common goal: to increase bandwidth while preserving cache line granularity. A bank group was introduced in DDR4. DDR3 only had banks, but DDR4 required much higher bandwidth, while DRAM core frequency and cache line access granularity could not be increased. Therefore, DDR4 grouped several banks into a bank group. Banks in a bank group operate at the same frequency, but data is alternated across different bank groups at higher effective frequency to increase bandwidth. Pseudo channels were introduced in HBM2, and they split the latest channel into two channels that share the command address path but have independent data path. This design does not require additional command address pins, but it requires careful interleaving of commands between the two sub-channels. So as a result, HBM4 now has a deep hierarchy shown in the figure. So however, this hierarchy introduces unnecessary complexity for LM inference. The first major issue is memory scheduling complexity. To read data, DRAM must receive commands such as act to read, read in a strict order while satisfying timing constraints. In HBM, many banks must be managed simultaneously, and each bank has its own timing parameters and states. The scheduler must observe all hierarchy level and decide which request to serve. So, and also memory controller also consider QoS and fairness, which makes the scheduler logic extremely complex. And the second issue is command address pin overhead. While data pins are continuously reduced, command address pins are difficult to scale down. So preserving cache line access granularity fundamentally limits memory system scalability. To address this problem, we propose ROM. ROM enables row granularity access, which simplifies the memory hierarchy and scheduling. And it also provides an efficient way to increase HBM bandwidth at low cost by increasing the transfer granularity from cache lines to rows, or between the on-chip cache to the MC. First, we introduced the concept of virtual banks to remove bank group and pseudo channel structures from the memory hierarchy. This illustrates the two pseudo channel structure in HBM4. This transforms the hierarchy into one that only consists of banks and increases the access granularity to the row size. Oh, let's start. This is the conventional HBM4. And we explored the three design options. The first doubles the data pins, but it increases the wire and buffer overhead. And the second pairs two banks within the same bank group. This avoids extra wiring, but still requires larger buffers. So we choose the third option. The third option is to pair two banks from the different bank groups, fetching data in an interleaved manner. But this requires no additional wiring or buffers and only increased row size. Since LMs already access data at kilobyte scale, this is acceptable. Therefore, we chose the last approach. Next, we eliminate pseudo channels. In the current HBM4 design, the data path is split into independent pseudo channels. The one option is remove them is to increase the data width, but it causes wiring and buffer overhead. And another option is to pair the two pseudo channels. And it increases the row size, but the LM inference is access granularity is kilobyte scale, so it is acceptable. So in summary, in HBM4, two pseudo channels from a pair and two banks from different bank groups form another pair. So 4 banks operate simultaneously. This set of 4 banks is called a virtual bank, and the access granularity becomes 4 kilobyte. Yeah, this is the virtual bank structure. And also there's many optimization, like we reduce the DRAM command as a row access granularity, so we only need read row and write row command, and we reduce the number of DRAM commands. And read row and write row requires only a fixed sequence of the commands, so only time parameter constraints between slave ID or virtual bank and read and write operation remain. These all parameters must follow the JEDEC standard. And also bank state motion can be simplified. And also we reduced the command order pins because our access granularity is row access granularity. So the time between each request is maybe tens of nanoseconds. It is not much longer than the DRAM column access granularity DRAM system. So we reduce the command order pins from 80 to 5 while meeting the critical timing constraints. And we put the command generator, which translates the read row and write row commands to the conventional DRAM commands in the HBM logic die. And we use the saved pins as the new memory channels to increase the memory bandwidth. In HBM4, one channel requires 112 pins, but ROM reduced this 107 pins. So we saving over 400 pins, and we use it as an additional channel. And also, as a result, the ROM increased the bandwidth by 1.125 times. More details, please refer our paper. And yeah, there is no limited time. So yeah, we evaluate ROM and HBM4 using LM simulator and Ramulator too. Yeah, this is, yeah. Oh, thank you. Ramulator's extensibility was essential here. We implemented both the HBM4 baseline and ROM interface within the same framework. And also ROM supports easy to use and easy to extend new memory system ideas. So we use Ramulator to evaluate our ROM across all LM workflows. And in terms of area overhead, ROM reduce the MC's area overhead to the 9.1%. And also the command generator has the negligible area overhead. And also we evaluate the performance, and then we evaluate some channel energy consumption using the Ramulator, but I'll skip this due to the limited time. Thank you.
So like over it. We can go over it.
Thank you. Yes. So to close, let me share 3 takeaways from these 2 case studies. I think first, DRAM Bender enables us to discover behaviors and constraints of real DRAM devices that are not visible from specification alone. Second, Ramulator makes it possible to explore old memory system ideas quickly, rigorously, and at scale. Third, they enables impactful memory system research by closing the loop between the experimental characterization and architectural design. So thank you for listening. Is there any question?
So I have thanks for the great talk. I have a question about DRAM school, right? Where we were talking about how the equipments are mapped into columns in a mat. Yes. Did you in DRAM scope verify this mapping you reverse engineered, or is it still hypothesized? That do we know, like, do we have the ground truth for a DQ, the mapping between the DQ signal and the position in the map. Also, it is data switch in terms of data switching. Yes, things. This one. Yeah. We reverse engineer for the first way. It's really difficult to figure out clearly. So we change the data, all the cells in a row, and then identify the data switching pattern. And also data switching pattern is different across the chips. Yeah.
Do you also release this mapping as part of DRAM scope, or?
Yes, we. Yeah. Okay. Yeah, we have the artifact evaluation, and you can check it as our code. Yeah.
Thank you.
Thank you. Thank you very much.
For the second work, as you mentioned, what was the improvement in terms of bandwidth? Can you explain?
Okay. The improvement bandwidth is due to we save the C pins because the row granular access pins, row granular access does not require such a large conductors pins. So we save the 13 pins per channel and aggregate it to make a new channel in the HP.
In terms of the evaluation, how much improvement did you see?
Okay. Maybe 9 or 10% of performance improvement. Yes, is
in terms of throughput or latency?
In terms of the TTF, what's that? The time per out token in decode stage. In previous stage, it is almost same because the previous stage, the characteristics compute intensive, so the ROM does not influence any other such a big effect.
And as part of the energy consumption, did you see?
Energy consumption, LLM inference access pattern is sequential access pattern. So there is the read per act is much higher than other benign workflows. So there is only few energy, how can I say, low energy consumption, but it is not big. It is almost same.
Interesting.
My question is actually very similar to the previous question. So is about with the ROM, is it more about it provides more bandwidth utilization as compared to the HBM here, or like it's like we have numbers for the utilization of the available like maximum bandwidth?
So your question is in terms of bandwidth. Can you speak on?
Like, yeah, sorry, it's like more about ROM is giving more utilization of the maximum bandwidth we have.
Yeah, right. That's right. But yeah, ROM gives a higher bandwidth compared with the conventional HBM4, but it access the DRAM as a row granular access. So there is a overhead from the overfetch, because if we want to read only 32 bytes, but in ROM we should access as a 4 kilobyte access per unit. So we call it as an overfetch overhead, but it is not critical in ROM because it is occurred usually in the self-attention layer, and if we also in small batch, there is only few, you can see that there's the portion of the attention is negligible. And then also if we increase the batch size, the attention's portion also be increased, but due to the large batch, the amount of access is significantly increased, and the overfetch overhead is reduced. So there is no kind of degradation of the overfetch either way. Thank you. Thank you.
I have one more question about ROM. So you talked about energy, but what about power?
you add 4 more channels. Does that also increase power consumption by? It is channel for one. It is power evaluation for one channel. It's not. It's 4 total channels. I see. Any other questions? One more.
So yeah, this evaluation is very nice. I wanted to know like how much does the bandwidth essentially improves for the memory itself rather than any performance for the device. Do you have any statistics for that?
Can you explain one?
So as you are actually reading more for each process and you are not adding more clock or more signals, so you require less signals. So it has less latency as well, like that. So if you have less latency, then should improve the throughput, right? Like just use the same system, update with your method with ROMs.
It's a great question. Can I ask it after this session? It might be quite a long. Thank you.
Thanks for the talk. I think you have done a very nice job. I like these 2 papers.
Oh, thank you.
You guys have done very nice work. One question I have on DRAM scope is, maybe this is like, what is left to reverse engineer after DRAM scope, you think? Is it all done or is there more to do?
I don't know well, but from now, as of now, I'm not. We're studying about like the DRAM scope stuff, but I think in terms of roll hammer attack pattern or roll press attack, there is many possibility to research, but I don't know well about the DRAM structure.
Okay, that's fine. Yeah. In terms of ROM, I think it's a good idea. It's good to customize the DRAM to workloads that are really important because DRAM designs a general purpose substrate. Right?
Yeah, right.
And what you're doing is customization for an important workload. People have tried to like reduce the granularity internally.
Yeah, right.
Also, have you thought about combining like ROM and some of those ideas where you reduce the granularity so that you reduce the wastage as well?
We're preparing like hybrid model combining the ROM and metal HBM4's the benefit because ROM's granularity access is 4 kilobyte. It's too big. Yeah. So for example, in nowadays the sparse rotation is important in the self-rotated layer, but in that case, maybe ROM have the less good performance, less performance. So we are preparing the ROM extension bigger and next submission.
Okay, looking forward to it. Thanks.
Thank you very much. Yeah, thank you for listening. Thanks, Harold.
So we're at the end of our workshop, our tutorial. I'd like to invite Professor Mutlu again for closing remarks, but he's now located in. You can do it also, you know. I already invited me, so.
This is called offloading work, I guess. Okay, I think we're done. We don't have. You have slides for me also?
No.
Okay.
I have better slides.
Okay, good. I think we're done. It's great that we had a nice attendance for this workshop, for this first instance of our first workshop. We'd be happy to get any feedback from anyone for the next versions. I think the next, when are we having the next version?
ISCA.
ISCA. So we will hold a longer version of this at ISCA. It's going to be a full day workshop. Which day do we know? First or second workshop day? First day. Okay, Saturday probably. So if you're interested in contributing, either people who are here or online, you're very welcome to have contributions. By that time, we will have released Ramulator 2.1 probably. So if you try it out, use it for different things,
we'd be very interested in learning your experience, and you can present it at the workshop. And if you need any help from us for DRAM Bender or Ramulator or any of our tools that we didn't discuss today that you can find on our GitHub, you can contact us on GitHub or via email. GitHub is easier probably because it gets seen by many people who are working on that particular infrastructure. So we'd encourage you to do so, but we're always happy to receive feedback and happy to support folks who are working on these important infrastructures. I think that's all I have. Anything anybody wants to say or any feedback? Okay.
It was good. That was conclusive.
Okay, we're done then. Thank you for attending. Hopefully we'll see you in one of the workshops tomorrow. We'll have two of them going on, one on virtuals and the other on memory-centric computing systems.
Good. Yeah, almost. We need help with.
Boya.
No, I think this is mine.
Teşekkürler. Bir şey soracaktım da bu Ramulator'da hani JEDEC'ten ne oluyorsunuz söyledin? DRAM timing restrictions ama. Yani direkt JEDEC'ten çünkü ben okumaya çalıştım bile yani ne var?
There was a problem. We just realized. Because I think this was on Nisa the whole time. I forgot to put this on the speaker. No. And we didn't see any
Comments.
yeah.
That is good and bad at the same time.
We'll see. Maybe she was close enough for the
To
microphone.
pick it up.
Aynen. İşlem ki önemli tutan bir şey almış aslında. Yok yani böyle hassasiyeti var.